Okay, good morning. Good morning. This is the official start of the first uh, week off. So this is a new model that we're using to run hackathons, and I should really stop. How do I put my themes on do not make sounds? I'll find out later. Okay, never mind. I cut that out in post-production. So this is a new model that I'm trying to test to bring hackathons to life. It's a bit of a different spin. What we want to do is to basically give people all the tools, like spend a good Monday just understanding and learning about the process, and then use that information to build something throughout the week. Um, I'm gonna bring all my team up. How do I do that? So I'm gonna bring Manas up. I'm gonna get Anson. Can you please come and present? And then we got a shit. Who am I missing? I'm missing Jose. I'm just sorry, guys. First time, like I said, first time we run this. Okay, I'm not sure you can see everybody. I think we're missing somebody. Anson. All right.
Anderson.
Okay, so this will. So I would like to first of all introduce my team. We have Manas Kumar, who is the person who will be leading pretty much everything, and then we have Ashit.
Yeah, hi guys.
And Sebastian, who are our interns at Deakin Launchpad. They're working on both their major thesis and also running an internship. And they will be helping you guys around. We thought that having some people who already have some background will make the teams for the week stronger, so that you all have something to work with. You're not starting from zero. Like I said, this is really the first time they're running it. We don't know if we got the difficulty level right, but we'll try to get there. So let's start maybe with the actual presentation. So perhaps I'm gonna kick Ashit and Christy out. Perhaps Manas, you as well. I'll just bring you up when you have to come back. So
Sure. Yeah.
Okay.
let me go and get my PowerPoint ready. Okay, guys. So welcome. This is the computer vision event for this year, brought to you by Deakin University, and thanks to also the Deakin Launchpad team, which I lead. So this is the agenda that I have also posted on Teams, so you can go through it. So today it's our intensive training day. Actually, the workshop starts at 1 o'clock, but we might actually start a little bit earlier since we have the time. The first workshop is going to be an introduction to object detection. Then we're going to have another workshop on using the TensorFlow APIs. Then we're going to have a break. And that's perhaps the time where you can start thinking about what would you want to make with the knowledge that you have now. 11:30 we start with the data preparation, which, as you probably know, is one of the most tedious parts of data science, and also the biggest blocker. We don't say that data is the commodity of the future for nothing. Data is going to be the most expensive thing that you can get. A data science project success is dependent on the data. You can have the biggest, greatest mind and the greatest algorithm, but if you don't have the data, you simply cannot do anything. So that's why we look at data. Then we're going to have 1 hour break for lunch. And once again, feel free to talk. We'll be here. During the afternoon, we will make a switch to another session. So I'll give you a new link on Teams. Please just follow it. And we'll bring you to another one of these Remo sessions. That's because the application only allows us to go for 5 hours. Then in the afternoon, we're going to look at the model configuration. And then we have another training session about training. Funny enough, we're going to have a break. 4 o'clock, Inference for 1 hour. Then a bit of time to maybe to talk to people. And then we're going to have our goodbyes. So it would be great to start talking about what you would like to do and maybe start mingling with people. Across the week, we're going to have dedicated support sessions at 10 o'clock in the morning and also in the afternoon. So you can just come in and say, look, I need some help or I need some guidance. Feel free to come in. Then on Wednesday, we're going to have another session in the afternoon about how to pitch a good presentation. And pitching AI presentations is actually a little bit different than pitching a normal application. That's because there are things that you need to know when you present. It's not just about the numbers of this is how much money we can make and this is the business model. It's about whether or not you can actually sell the idea. And the idea of AI has very specific things that you have to say. On Thursday, I'm going to run a session called AI as a service. And this is probably very good for those people who also want to specialize in cloud computing. Everything that we do about AI is probably going to be running on Colab or in your own system. But the truth is, nowadays, you need to know how to use the actual AI as a services. Because one, they make your life much better, they allow you to scale, and well, they're already prepared. Why would you want to go and do it all over again if you don't have to? It's the difference between making it and not making it. And we had to do some work on it. So, and then on Friday, we're going to have you guys pitching your ideas. So that's hopefully going to be the fun part. We have some gift vouchers to give away. So let's try to, we want to give them to you guys. I can't have them for myself. Yes, so that is the agenda for the week. Let's move forward. Your host for the week, me. I'm Dr. Alessio Ponti. I am Director of Innovation for the School of IT. I've been at Deakin actually for longer than you guys can imagine. I was actually a student here since 2007. I left when I finished my PhD in 2012. I joined a small company called IBM. I was part of the research team there for 6 years. And that's where actually I got to start working on computer vision as a research software engineer, leading prototypes and really work with the startup environments. One of the largest projects that I actually worked on was the first use of computer vision for detecting skin cancer. So that was a huge thing here in Australia. I am also the co-founder of the Deakin Launchpad, which is a team inside the university which deals with rapid innovation and startups. With me is Manas Kumar Palaparthi, who is the current AI lead at Deakin Launchpad. He was actually a student doing his master's of data science just last year. He, I guess, is one of those really big surprises that you find, really dedicated to computer vision to the point that, well, he's still here working on computer vision projects. So, yeah, very glad to have him. And he's very knowledgeable and very passionate about it, which is the key thing here. Just some of the examples. These are the things that me and Manas worked on just in the last 4 months. So we've been working with this company called Save Synergy, not Energy, I made a mistake there, to build a tool for detecting compliances in the managed facilities like warehouses or in the train stations to find out if people were going out of bounds or doing the wrong things, running, not wearing safety vest or similar things. Then we have been working on a project called Blue Balloon, which is a collaboration with Monash, La Trobe, and Harvard University around the use of computer vision for autism detection in kids. We have been working on some of the current data sets, and 2 weeks ago, I think we managed to get a better 2% increase than the state of the art. And currently, we're working on another project called Measure Up, which is a tool for using both computer vision and AI computer vision and another part of AI to create 3D avatars that will be used in the fashion industry. So that's another project that we're running with a current startup. So yeah, we're very active in this part. We are very product focused. Some of the activities breakdown, we already went through this. Monday is intensive training. Tuesday, team activities and support. Wednesday, we have workshops. Thursdays, we have support, and maybe you can rehearse if you want. And Friday, we have the competition. What do you have to do? So you are here today to get training, and then during the week, you will be forming a team and work on your own project. And we're here to support you. How much time do you need to dedicate? That question came up. The answer is as much as you want. Just be very upfront with the people that you work with and say, look, this week I can work these days. I can contribute this much. Do not give the wrong idea to people. Overall, we're here to have fun and to learn. So those are two of the key things. Even when we see your project on Friday, we're not expecting something finished. We want to see a good idea and allow us to dream of what you can do with it. So your group, at the end of today or tomorrow morning, you will get together in a group, and I would like to know where those groups are so that I can allocate my resources as well. And about your project, what projects do you want to solve using computer vision? We're here to learn. Remember that. Think about the following, perhaps. How impactful is it? What are the risks of bringing this project to life? And the last, but also not least, is it fun? Is it something that you guys are interested in? So these are the three important things when you make a decision about where you want to go. There are some ideas that we're looking at. So for example, we want to do fish detection because currently we have a number of projects which are going into that direction. I believe that Kalia might have had some ideas because she's running a few projects. There were so many things. I talked to different people during the week. So be open, try something that you haven't done before. Pitch. You have to prepare a 3 minutes presentation for the judges. In those 3 minutes, we want to see what your project is about. You will have more time to do a demo as well, but the 3 minutes is for you to say, what is this project about? What are the three things we look at? We look at innovation. Is it something innovative? Or is it just copy and paste? If you go and do a dog detector, that may not be the greatest innovation in the world. Feasibility. Is it actually possible? Can you actually go and do it? Is the data readily available? So perhaps if it's something where the data is readily available, then your feasibility will be really high. But if it's something which is really complex, like in our case, the autism detection, where we are dependent on medical data, the feasibility is actually quite wobbly. It's quite risky because we may not have the data. And then we have, how well did you present? How much did you impact the judges? And I think I'm going to leave here. Before I move forward, first of all, I'll bring Manas if you want to join back in here. I'm going to clean up the Q&A. How was your day? My day was good. How are you today? I'm good. Can you see my question? Yes. Where was the lockdown end? I don't know. You cannot see me. No, I cannot. I could not see the link. I'm not sure what that is. Yep. The workshop's recorded. Yes, we're going to record all of the workshops. So everything will be recorded.
Yep.
Okay, so before we move forward, does anyone have any questions that they want to bring up? Okay, so things that I want to remind, you can easily go into the, when we're not in presentation mode, you will be on your tables. Within your tables, you can talk among people, you can move from one table to another table. You have a number of things that you can do, like bring up a mirror, a board, or a whiteboard. So there's quite a lot that you can do. It's quite fun. It's quite this this environment is quite good. So I think I'm gonna leave it to Manas now to lead the way, and yeah, off you go. It's all yours.
Sure. So good morning, everyone. Again, yeah, today it's going to be a bit of computer vision, basics of computer vision, and stepping into solving problems using computer vision. So I'll be more focusing on object detection today. However, this is just one small part of the entire computer vision. And one second, how do I change slides?
Yeah, Manas, you probably want to go and start sharing. Do you have the slides? You should have them.
Uh,
No, don't. Okay, just get the slides up. While we do that, I'm gonna post a link for the team so where you can find everything. So okay, we're just waiting for Manas. So there's a few things that you need to take care of. One is there's a Git page that Manas prepared where all the information is. And the other part is the team page, which I'm gonna link now. And I lost Manas. What happened to him? I'm not sure. He's probably just trying to get. Okay, back to you. I think you're muted. Manas, you're muted.
Hello?
Okay, all good. All back to you.
All right, yeah. Perfect. So I'll give a small introduction of what object detection is. So previously we have learned about image classification, of basics of image classification, which is recognizing an object if it, and classifying them if it's a dog or a cat. However, comes is with localization. So object detection basically solves the problem of localizing a, a class. Suppose you have three classes over here: dog, cycle, and a car. What object detection does is it does image classification. It detects what the object is and also detects where the object is. So it's basically solving two problems at once. And so that's where we call detecting the boxes is a regression equation, and detecting which what's the object is a classification. So it does two things at once. And I'll again quickly go back to my slides. Yeah, so there are various object detection models really readily available online for us to like quickly download them and start doing. So one of them's were one of famous object detection algorithms were SSD, YOLO, Detectron is basically by Facebook, and object detection is by Google, TensorFlow. And yeah, so all these models are pre-trained models. They're all deep convolution, deep neural networks, which are already trained on large data sets such as COCO or ImageNet data sets. And these are uh, very huge models. The current state of the art models are also included in these APIs that we can use. And yeah, applications. Where can we use object detection? Uh, so we can use them in real-time applications, video surveillance. It's basically everywhere. So whatever we can imagine doing with it, it is possible to implement in every scenario. Uh, it's all that we need to care about is the data, how we collect data and transform our data into a proper a detection algorithm or something like that, right? And yeah, advantages and disadvantages. So there are many advantages for the object detections. One is machines cannot obviously recognize things without having a camera vision to it. So once we have a camera vision to a machine and we enable it to basically detect all the objects, whatever it sees, it's a much more, I mean, you are enabling a machine to look at how humans look at objects, right? And yeah, that's the huge part of the advantage, that you can see objects, machines can see objects and classify or detect them. uh, Basically, do lots of things with once we detect suppose a person, we can do a lot of things. We can track the person, we can identify a person, we can basically label that person and make sure where exactly this person is moving, anything like that. And yeah, disadvantages. So at the end of the day, object detection is still on a video or image or something like that, right? So what happens is all we are doing is just doing a drawing a box around the object and basically saying this object is localized at this particular point in the picture, but we exactly don't know in real life where this object is. We couldn't understand the environment. So if it's a road, we can still classify it as a road and say there are so many cars on the road. However, we don't know how far they are, and we don't know the 3D geometry of that environment. So that would be a huge limitation just using object detection. But that's where the other technologies come into the picture, such as LiDAR and other SLAM algorithms. All these come into the picture to basically detect an object and also check how far it is from your location and do all that stuff. So yeah. Yeah, and the other thing I wanted to mention is like the data sets. Usually all these pre-trained models are all trained on only two data sets, which is ImageNet dataset, and the other one is a COCO dataset. COCO is a common objects of context, and the ImageNet dataset is basically ImageNet is basically a very large dataset of around 120 or more than that. So there's so many images and so many classes. They're all images from all over internet, YouTube videos, everything. And yeah. So in this workshop, what we'll focus is the object detection API from TensorFlow. So I've choose this because we have an end-to-end pipeline where we can gather data, we can basically prepare our data generators, pass it to our models, pre-trained models, and train our models in a really good, uh, I mean, really feasible way, and then export these models for real-time protection. We can either use it in a mobile phone, or we can either use it on a web application like that.
I think, sorry, Manas, just before we move forward,
Yeah.
can you just go back one slide?
Uh, oh,
I think it's probably just stop sharing for a moment. Don't run the slides from here. Just run the slides from PowerPoint normally.
yeah, yeah.
Yeah. So yeah. So guys, so computer. If you imagine this, computer vision is part of the larger science, which is cognitive computing and cognitive science. So cognitive is basically, the ability to give machines human abilities like talking, seeing, hearing, and so on. Um, Now, the one thing which is important is to try and understand what kind of problem you want to try and solve. And that's where your creativity and your innovation comes in. Um, so, and I think Manas mentioned one thing which quite well. The data sets, most of the data sets are actually pre-trained. So you can use either the Coco or you can use ImageNet. But you will find that although you can do quite a lot, it generally doesn't really solve your problem. So, for example, it does not solve our autism project. It doesn't solve our um, image health, the health and safety project, because we don't have images of specific classes. So that's where the problem comes in. That's where you guys have power to innovate. If you have a problem, then you can start perhaps contacting people um, who might have that data. The one thing that we always found out about computer vision is that everybody talks about computer vision, but not everybody actually does something about it. So you will find a lot of people making papers, but not actually making products. So you will find, the greatest algorithm on 2 minutes papers, but it actually just gets abandoned. It's a nice paper, everybody talks about it, but nobody comes up with a product. And that's where you guys might come in. So don't just think about a paper in a scientific way. Try to solve the problem that you have next door. Try to solve your own problem. For example, there was one time that I wanted to find all the stray dogs in the community, and my idea was to basically do a geolocated query on or everything which has pictures like Twitter, Facebook, Instagram, geolocate them and find dogs. So I wanted to find the stray dogs so that I would have had more information that I could give to people. So this is to say, the ball is in your court. You have the ability to do all of these things, which is, as Mana said, it's not just the finding where on the screen it is. We have learned to do much more than that, which is, for example, doing the depth. And that was
Yeah.
something that we couldn't do 5 years ago. Now we can do quite easily. So do you want to give an example of the depth, how you used it?
Yeah. So there is one more problem apart from object detection, which is called monocular depth estimation, or simply we can say depth estimation. So depth estimations are algorithms uh, that basically predict depth from a given RGB image. So we can find uh, how far a pixel is from the picture. So we can exactly know what's the distance between this pixel to the camera. And combining with this one with the object detection, suppose we classify this box as a car, and now we know how far the car is from the picture. So computer vision is a combination of different tasks put together in a meaningful way to uh, solve problems, basically.
Okie dokie. All right. I guess so. we can go for the next part of the workshop. And then after the next part, guys, it's really you need to start a conversation with us. Maybe start thinking about what kind of problem do you want to solve, and let's start discussing it, because that's what we're here for today. If we just wanted to go on, we could have just done our projects, but we're here because we want to see your projects. We want to see your ideas. So talk to us. All right, off you go.
Yeah. So yeah, I was talking about the data sets. So usually all these data sets are trained on the ImageNet or a COCO data set. These are very large data sets, and they provide our initial models to be good enough that we can use them for our later purpose. So we call this method as transfer learning. So we train our model on a very huge data set that is readily available, and then use that particular model and train it on a smaller data set for a specific task, and still achieve a really good accuracy. And yeah, a small introduction on object detection API. I'll quickly show what object detection, TensorFlow object detection API is. So, yeah, and this is the official TensorFlow page for object detection. And yeah, it supports the older versions of TensorFlow and the newer versions, which is 2.5 currently, but they still support the other versions as well. And yeah, you can find all the instructions of how to use these models, everything, and I'll definitely go step by step when we are doing the workshop. uh yeah, so 1 second. So the object detection, I mean, the main API consists of these three things. So the first one is the model zoo itself. So object detection model zoo is nothing but a list of pre-trained models. Uh, Basically, you can choose it from here. Or for TensorFlow 2, you can go to the model zoo, which is this one. Yeah, so this is a model zoo page where you can find all your pre-trained models. So I won't go deep into what the model architecture is for each and every one, because these are really complex models, and you need a bit of statistical background to understand what exactly these models are. But at the end of the day, what they provide is this. So this is the accuracy. So this is the accuracy on COCO dataset, and this is the speed and what they output. So boxes is nothing but, as we have seen in the before pictures, the boxes is bonding boxes on objects, and key points are nothing but pose estimations, something like this. So these are called key points, and I guess they have like 17 key points for humans, and different models have different key points. They basically denote the bones of the postures. They also work with animals. Few models are trained with animals, and few of them work only with humans. So yeah, so there are so many models to choose from. So I'll let you know how we can choose. I'll quickly open my calculator. So here you can see the speed and the accuracy. How we can calculate this is basically 1,000. This is in milliseconds. So 1,000 by, you can say, suppose you want to use this model. So that's 197. So it's going to give you 5 FPS, 5 frames per second, which is not I mean, it's partially real time. It's not real time. And there are some models which give really good frame rate. suppose say SSD mobile nets. They are lightweight models generally used for mobiles and uh, lightweight equipment such as Raspberry Pis, Jetson Nano, all these equipments. So if you have 19, that's basically 1000 by 19, you get around 52 FPS. Uh, yeah, and they output boxes. You can also see this particular model, which also outputs a mask. Mask is nothing but a semantic segmentation, which is this. So it'll just not draw a bounding box around an object, but it'll also classify each and every pixel. So how these pixels are mapped to an object. So it classifies every pixel uh, and also draws a bounding box. But you can see these models really take a really long time to give us the results. All the semantic segmentation models are computationally really expensive. So they need a bigger GPUs that can handle, such as Tesla P100, or yeah, kind of NVIDIA Quadro 6000 series, some really high-end GPUs to basically handle image segmentation. That's a small introduction of the model zoo. We'll definitely go into this once we are doing the workshop. And yeah, we'll later on uh, go and see how we can install this API on Google Colab. So I'm making this really easy to implement on Google Colab, because we can completely avoid uh, installing drivers for Cuda. So if you want to run TensorFlow GPU on your machine, you need to have a GPU, dedicated GPU. Plus, the GPU should be so compatible with TensorFlow version and also the CUDA. So it's a really big process that we can completely skip by using Google Colab. And later, yeah, we'll go through the data preparation. The data preparation basically consists of formatting your data. So data is nothing but image, and you have some data with associated with that image. So suppose say you have one cat and one dog in a picture. So this XML files will basically have the same data, that is one dog and one cat, and the bounding boxes for each and every object, and how we process them, all these things. And finally, yeah, we'll go and see how we can download these models, how we can edit them, train them. Yeah, I dedicated a really good amount of session for training itself, and so that includes training from scratch, fine tuning it, and also checking our results, selecting our best model, how to stop training and select our best models. And the last part is would be the inference. So once you have a trained model, how we can export these models and use them for production. Yeah. So in this workshop, I'll focus on using this trained models just in the Colab itself, because it needs a GPU to run. But later on this week, I will introduce uh, TensorFlow JavaScript and TensorFlow Lite as well for mobile development. And I'll also tell you the difference between the GPU inference and the CPU inference. Let's quickly get to the Colab notebook. So this will be a Colab notebook that we'll be working on today. I'll share the link for this one in the group. You guys can download it, and Yeah, open it in Colab. So what I'll do is, uh, with you, I'll start doing it, doing the entire thing from scratch so that you guys can follow up and basically replicate it. Just give me a second.
Okay, so Manas, how are you planning to do this next part? Because we've already been talking for 1 hour, so maybe what we can do is to,
Yeah,
no, we've been talking for less than an hour, 45
yeah.
minutes. So do they need to get something like done? Do they, perhaps, should, I was thinking of giving people maybe 10 minutes or so just to rest and to perhaps talk, and then,
Uh, yeah,
or
100%. Or they can probably visit these all websites and check what they're offering. All these things. I'll just link all these websites in the chat itself, so
yeah.
people can. Yeah.
So I guess, guys, it's important perhaps that you go and make your Google Colab account. Um, should we give a? Have you explained what Google Colab was?
Uh,
Perhaps we give a small intro.
yeah. So Google Colab is nothing but your Jupyter, a kind of your Jupyter notebook where you can execute Python code, just like you do it in a, Jupyter notebook. However, in the runtime, there is an option called change runtime where you can select GPU. However, there is a limitation of using these GPUs. You can only use it for like 7 to 8 hours, and that, I mean, that session would at least reset within 28 to 48 hours, 24 to 48 hours. We're not sure about when it would reset, so I suggest you guys to have a couple of Google accounts with you so that you can, in case if the GPU runtime ends its session, you can quickly jump onto a next account. However, for storing stuff, we will use our drive itself, our Google Drive. We can link our Google Drive directly onto the Colab notebook, and we can save all our models, data, everything on the drive, and use it from the Google Drive. And yeah, I will go through the procedure how we can do that step by step uh, with you guys. So I'll, yeah, this notebook is just for the reference part. I'll anyway start an entire thing from scratch, explaining every line so that you guys can follow it and also implement this for your problem. All right. So this is going to be our notebook for the workshop. So what I'll do, I'll try to quickly switch my account firstly. Yep. So I think this account has a really, I mean, I haven't used this account for the GPU. So the first thing we have to do is change the runtime. Yeah, for those guys who are not familiar with Google Colab, so I'll do a small introduction of Google Colab, how it works. So on the left side, so initially it's basically allocating a virtual machine for this. You can see here. So you can see here we have around 12.69 gigs of RAM. It allocated some 68 gigs of storage, and we're not sure about the CPU, which CPU or which GPU it has allocated at the moment. So runtime, change runtime. You can either select GPU or TPU. So we need a GPU for this project. So we'll go and select GPU here, save. So now it will reinitiate our virtual machine. And yeah, so I think we are connected with the GPU itself. You can see here GPU. And yeah, So this Google Colab, we can use our cloud storage, our drive storage within this hard drive. So what you can, in order to do that, there is a option here, which is a drive option, a drive folder. And yeah, this is a simple search where you can search some keyword and basically replace them just like you do it in the Word files, all these things. These are how we, sorry. So yeah, these are basically fields, form fields, how you can add them. Yeah, we really don't need them much. So suppose you're doing anything about date, how basically you can use them. Yeah, not so the important part is this one, the files, this folder. So this folder is basically how we navigate our things, navigate our directories. So we'll quickly go ahead and connect to the drive. So drive. So in order to connect, we can just click on this one from Google Colab, import drive. We mount our drive, just click on this one. It'll redirect to our the Google Drive account. I'm going to use mine, sign up, and it'll give me a code like this. So I'll copy this code, go back to my Colab notebook, paste it, and then enter. So I'm mounted to my drive here. So also I can see it over here. So I just need to click a refresh button here so that everything gets refreshed, and then we can simply use our all the drive files over here. And on the other page, I'll simply open my drive, Google Drive account, Google Drive. Just changing my account. So yeah, so that's my Google Drive, and yeah, there's nothing related to this project yet. So we'll go to the drive. It's basic Linux command, cd space the folder name. We can simply get that using this copy path, and that's basically that. For everything, so for navigating locations, you can simply navigate it on the left side and use that copy path option to basically copy its path. Okay, and now we are going to the drive folder. So I've created the necessary files. Oh yeah, sure. So I think you have the link for the. So we have a question in the chat. They couldn't manage to open this file. So when you click on this file, it'll open a page like this. It's a GitHub just page. So you can just click on open in Colab, and it'll redirect you to open this file in Colab. I hope that would answer your question. Yeah. All right. Yeah, sure. So there is one. So I've created a repo for this project. So this repo will consist of few important files that are required for this project. I will explain what these files are in detail later on. So we have to clone this repo. So this repo is a Launchpad repo. It's in launch. So where we can find this is basically here. So this is a repo. object detection workshop, CV1 workshop. So what I can simply do is code, copy. I can copy this link, and go to our Colab notebook. We can simply paste our link like this. You need to have an exclamation mark to execute this as a Python, the Linux command. So you can simply do git clone this website, this link, and then it will clone the entire repo in the drive folder. So the current directory that we are working on is my drive. My drive is default for everyone. So when you connect your drive, it's going to be the same structure: drive, my drive, and all your files in your drive. So when I do this, when I refresh it, so there will be a folder like this in my drive. I can also see that when I open my drive, these are all the files. Okay, that's done. We'll go to this working directory. So we'll change our working directory to the CV1_workshop. Simply do cd space your working directory, next directory, and this is the path that you are currently in. To always check in which folder you are in, you can simply type pwd, and that would give you the present working directory. Yep, and yeah, we'll quickly go and install the TensorFlow. So there are a couple of steps that we need to make sure that the TensorFlow is properly installed. So for this, make sure that it's TensorFlow GPU version of TensorFlow that you're installing. Before this, I just quickly want you guys to know the TensorFlow installation part directly from the website. Free TensorFlow GPU. Yes, so this is the main TensorFlow website for GPU installation. You can simply install it using pip install TensorFlow. However, this will install the current version of the TensorFlow, which is the latest one. I guess it's 2.5, 2.5, 2.6, and the current version is not supported yet by the object detection API, and it's still in the beta. So I would advise you guys to use a stable version of TensorFlow, which is either 2.3 or 2.4. I've tested the entire thing on 2.3, and to install a specific version, you have to specify it like this: pip install TensorFlow-GPU 1.15 or 2.3, something like this. And for those people who are trying to install this on a laptop that has
Manas, wait a second. So
yeah.
we have a few questions. I still don't understand how you open the page in Colab.
I think I explained that. Yeah.
Oh, did you already look at the questions?
Yes.
Okay, then kill them off.
Okay, yeah.
Yeah,
I'll make sure I move the mouse slowly as well.
Okay.
I'm using a pen mouse, so it's really fast on the screen.
Okay, I'll leave it back to you.
Yeah. So if you have a dedicated graphic card on your laptop, you can follow this instructions to install Cuda, and yeah, you need to follow the actual step-by-step installation of Cuda. To skip everything, we are trying to use Google Colab as our platform for this workshop. It's a tedious process to install all these drivers and get the proper version. So in order to get the proper version, you can simply go TensorFlow GPU, TensorFlow Cuda, CUDA, chat. And when you go to images, you can find so many images like this. You can open one, and this chat will tell you which version of TensorFlow supports which version of Python and the compiler. And you can also see this is CUDNN, the CUDA version, and this is CUDA, CUDA. So you need to match all these things, all the four things, in order to make sure that it's working on your uh, laptop or a desktop. Yeah, and that's some basics of how we install GPU TensorFlow. But in Colab, it's pretty much straightforward. Colab will handle everything for us. Just click on pip install TensorFlow -GPU. This thing, it would take some couple of minutes.
You have made a step-by-step of this on the task, right? On the GitHub.
On the GitHub?
Yeah, do we have
No.
instructions like step-by-step?
Yeah, people can actually follow this one itself. So
okay, yeah.
Yeah, within this, I made it like a step-by-step process.
Yeah. So this is probably where, and I think even by experience, getting your environment to work, even following all the steps, doesn't mean that you will get the environment to work. Because it is not a kind of Windows double click and everything magically happens. It's dependent on something else, which is dependent on something else, which is dependent on something that you never heard of. So yeah, we've been there. So that's why perhaps we're using cloud environments, it's really a good part, which is why, for example, Amazon is pushing SageMaker a lot. So generalized AI as a service. So Amazon has AWS. Amazon has SageMaker. IBM has Watson. I'm pretty sure that Google probably has something with a similar name. But everybody is going to do this, is trying to do this, because it is terribly difficult to get everything to work. I think even us, when we were trying to install everything on Windows, we had to like just hell on earth. There's a huge error.
Yes. No, that's fine. That's fine. It's not actually an error. So yeah, on my screen you can see the same message that you have to restart your runtime. That's because when we install a GPU version of TensorFlow, usually in Linux machines or Windows machines, we need a complete restart. So simply here, what we do is go to runtime and click on restart runtime and then say yes. So now it will reinitialize your virtual environment. Probably you will get a different, completely new virtual environment. However, the before cells that you, all these cells that you worked on, they're basically your drive. Your drive location didn't change. And again, make sure, you're still connected to your drive, and you still have, that means you still have all your files, but you just restarted your runtime. And then just click on, do I need to connect to a local or a hosted runtime? So here, it's a hosted runtime. We are not using local machine. It's a hosted runtime. You can simply click on runtime here and then restart it. We don't have to select it from here. And so once that's restarted, so it's just again click on this pip install. Now it will simply say requirement satisfied. That means it already has the TensorFlow 2.3 in the background. Just for confirmation, you can import TensorFlow as TF using this, and simply check the version using version command. So running this will basically give us which version that we are running on, which is 2.3. All right. Now let's go and clone the entire TensorFlow repo. So in order to in order to use this API, there is a huge TensorFlow repo, which is this one. Sorry, one second. Research models. Yes. So this is the main TensorFlow repo. You can simply type TensorFlow models, and then you will get to this point, and you can. We have to clone this. So this repo will not just have object detection. So in the research folder, there's so many other tasks as well. So you can see LSTM object detection, which is nothing but it uses sequence of frames to do the same object detection tasks, but it will take multiples of frames. It is good for videos or action recognition kind of stuff. And it also has other uh, video to depth, other models, video to depth. There are so this is a text recognition model. This is the deep speech. Deep speech is basically analyzing. It's a speech synthesis model which will analyze your. It will convert your voice to a graph kind of structure, which is called as spectrograms, and they use spectrograms to process speech synthesis. So there are so many other projects here, but the one which we are concentrating on is the object detection. So the object detection has, I mean, so many files, so many happening on this particular repo. It's a really large repo, but I'll break down stuff and make it as simple as possible. So you can go through this repo and check basically what TensorFlow is offering for object detection stuff. Jumping to my Colab, I'm simply cloning the entire repo, which is TensorFlow and models, directly onto my working directory. So I'll make sure that I'm on my working directory, which is cv1_workshop, and then do a git clone of the entire TensorFlow repo. This should create a folder underneath this. It usually takes a couple of minutes because it's a very large repo. There you go. It's almost there. You can see. Also, guys, while using this Colab, so I suggest you guys to, I mean, touch this interface. I mean, just touch this interface for every 2 or 3 minutes, because it's running on it's just a website, or if, when you keep this page ideal, so the entire virtual environment which is created might shut down, and then you have to do the entire creating your Python virtual environment and creating all this stuff again. So I suggest you guys to uh, not show, I mean, continuously interact with this Colab notebook. And here you go. Here, there is a models folder that you can see. And this models folder is nothing but this one. It's the same one. We just copied the entire repo. Yeah. And inside research, you'll see object detection. And these are all the object detection files that we needed for this workshop, right? Awesome. Now, once I clone this, I'll go to the research folder. So now my working directory is the research. I'll just execute this. And now I'm in my working directory. So when I go to this research folder, here, there is uh, so object detection as well. So inside object detection, there is a folder called Protos. This is the one, Protos. So these has so many files in it. And you can see there is an extension dot proto. So these are proto files, I mean, the necessary packages that TensorFlow needs to run them in the background. And you have to install all these files to make sure that your object detection API is installed properly. So in order to do that, you can simply type this command. We are using protocol buffer, basically a package to install all these .proto files. So this is the path, and star is for basically selecting all the files which ends with .proto, and yeah, you're basically installing them. That's done. And there is a you have to clone this Cocoa API as well. And this Cocoa API is basically has all the necessary packages in order to deal with models that are trained on Cocoa dataset. So you can see in the model zoo, in the TensorFlow model zoo, where is it? Research, object detection, and TensorFlow model zoo. You can see almost all the models that in the list are basically trained on Cocoa. So right now, it's a Cocoa 2017 data set. So we need that Cocoa repository as well uh, to work with. And being in the research folder, make sure that you're in the research folder and then clone this repo. Yeah. Once you clone this repo, you will create this folder within your research folder, which is maybe I have to just refresh that thing. Now you can see it here. You can see it here. And you have to basically build this API. So make sure that your working directory is Python API within this Cocoa API. You can just click on this and make it. And this would take a couple of minutes to install it. Yeah, that's done. So we've installed the Cocoa API as well, and we are just checking out where we are exactly in our system. So we are exactly in the Python API, which is here. So the next step is basically to copy our protocol tool. It's a package which is this entire thing to our research folder, right? And just copy them. Second, that's because
Hate when I talk and it doesn't work. Manas, do you want to just do
yeah,
a one plus increase on the font size?
yeah, sure.
To one zoom in. Yeah, I think it will make people's life easier. Um,
Yeah, can you guys see it
and
now?
also, guys, please feel free to ask questions or stop halfway through. I mean, we're here to make
Yes.
sure that everybody understands. So,
Yes. And any questions, any doubts, you can quickly post it on the QA session. I'll quickly go through them as we go.
we do have lunchtime available. So, you can kind of
Sure.
catch up on lunchtime as well. But yeah, feel free to ask the questions because otherwise,
Yes.
just ask them.
Yes. And yeah, in case if you feel you have lost somewhere uh, in the tutorials, please let me know. I'll address them as soon as. So, do you copy the CV1 underscore workshop into the drive before anything? So we are doing this just using this command, and this is the repo. So CV1 underscore workshop is a repo within the launchpad, this one. And these are all the necessary files that we need for this workshop. And simply just clone this using this command to your drive. The other way is
One
simply,
second. I just noticed one thing. That's how
yeah,
a Deakin Launchpad GitHub. Has anyone tried to access this? Can you guys actually see it?
yeah, it's a public one.
Okay, so just making
Yeah,
sure because yesterday you asked
yes,
me to try it, but I am the owner of the whole organization, so of course I could check it. So yeah,
yes.
just let us know if you can't see it.
Yes, I think I'm accessing this from a different account, which is not from the Launchpad. So yeah, I'm sure. Yeah.
And I think there were also other questions, starting with Arun as well. So not CP minus R per whatever. Yeah,
Where can I see that?
in the chat.
In the chat.
Yeah. So guys, if you have questions, it's also better if you just put them in the Q&A so we can actually
Oh yeah.
cross them
Got
out.
it. Yeah.
So one thing was not CP minus R
Oh
Python.
yeah. So I did a mistake there. I just put a space here, so that basically messed up. And where is that again? All right, so here. So if I run this, now this should work, because before I just put a space by mistake here, and it's just my drive, and there's no space there. And yeah, that copied this file. So I would say this is just the cloning part of the entire object detection to your project. Now we have to go and install all these files. So right now we just clone them. We installed few of the dependencies, which are protobuf files. Now we'll go ahead and basically install the object detection API itself. Okay. Let's make sure. So the current repo is, the current working directory that we are in is Python API, which is from this one. But to install the object detection API, we should be in the research folder. So research folder is our main root folder. We have to be there. So CD and the entire space, entire path. Now we are in the research folder. Now I'll quickly go through this one. So in the object detection, and you can see packages. So now you have two, TF1 and TF2. So this is for TensorFlow 1, TensorFlow 2. Simple. So when we click on TensorFlow 2, there is a setup file. So this setup file, so any py file, if you want to open this py file, just double click on them. It will open on the right side. So this is how we are going to edit Python files. So this setup file, it's nothing but it has all the packages. The Python necessary packages, such as your pandas. This is your TensorFlow model zoo. Your TensorFlow installation, all these things. we already installed them the proper way, but this is a different way of installation of TensorFlow. I wouldn't recommend this one because this is very specific to the API, but the way which we install TensorFlow is generic and can be implemented for other projects as well. So yes. Yeah, these are the few installations that you have to run. You don't have to change anything here. Just close them, but we have to run these files using this command. We just copying that file first. We copied that file and then installing that file. This usually takes around a couple of minutes because it has to download few packages. So this this command will nothing but make sure all your dependency packages are on the right versions. Suppose say you're using a very latest version of NumPy installed on your notebook, but that particular version doesn't support your TensorFlow object detection API version. So that would again create a huge problem, and you don't know which version of NumPy is supported. So that setup file will automatically install all the necessary packages with the right version. Yep. The next step is to test our installation. So this model builder underscore tf2 underscore test will basically test if our object detection API is installed properly or not. You can spot this file in the object detection folder. So when we go to the object detection folder, that's builders. So where is builders? And there's so many files here. And you can find model underscore builder. Where can we find that? Model underscore builder tf2 underscore test. So just click on this one. And this one will basically test firstly our GPUs, if we have a GPU or not. And if we have a GPU, then it will go ahead and test all our all these files on the GPU if they're built properly or not. So successfully doing this will ensure that your Python environment is configured using configured for object detection. So it's going to do it on all the models. You can see SSDs, efficient model, efficient net models, and
we got Makara, who is that the same error that we got before in the Q&A?
the dependencies resolved does not currently take into account all packages are installed. This behavior is the source of the following. I haven't seen that error before.
Okay, we can try to go through.
Oh yeah. So yeah, you can definitely skip this. So I think this is the one. Yeah, you can skip this. So what happens is when we install all these packages, there are so many packages which are not compatible with the other ones, but they're not mandatory for the current project. So you can see here it says incompatible, but still it works. It still works in the background. We can see by using this test folder. So when we do all these tests, it also gave us an error, but the error was just one. So out of all the files, it just gave error for one file, which is for uh, Not sure which exact model file it is, but maybe efficient net, building an efficient model. We can ignore that because efficient nets are still in the beta versions of development. Uh, I mean, they are the state of the art models, and probably we cannot train them on the Colab. They need multiple GPUs, at least 4 GPUs to train them. And yeah, they're really computationally expensive. So yeah, we can completely ignore them as we are not at all using that model. And let's go to the selecting pre-trained models. How we select pre-trained models? This is our model zoo. When you click on this, it will again redirect to our model zoo folder. So until this point, we have successfully installed the TensorFlow object detection API, and now we can simply start working on our uh, our problem. I mean, our a product or a research problem that we are trying to achieve. So first thing, I mean, this is definitely not the first thing. I just put it there. However, the data pre-processing should be your first thing. Data data should be your priority to start with. Uh, yeah, why not? I'll just skip that down and put the data processing up. And let's go ahead and start how we create data and what type of data we can use for this object detection API. Okay. Obviously, images. Suppose let's take an example. So I'll take an example of construction vest. So my problem is I wanted to detect construction vests and construction hats. If a person is wearing a construction hat or is not wearing it. So I just two classes, which is wearing, not wearing hat, right? And I have a data set on my own. I mean, so it's already done. So everything, all the data sets are done. However, I'm going to explain how exactly we can create our own data set. Suppose you have a very specific, uh, I mean, you want to create a very specific product, such as recognizing medical equipment. You may have the data online available, or you may not. But in case if you wanted to create your own data and you have the medical physical equipment with you and you want to create a data, I'll show you the procedure for that. Suppose say these are all the images that you have. Uh, so yeah, these are all the images that you have. They can be downloaded from internet, everywhere online. You can scrape them from trusted sources, licensed sources, and put them all in a one folder, such as I've simply put it in the image folder. You can put it there. Now what you have to do is simply, there is one Python package which is label image img. So this is a Python package, label img. We have to install this on our local system because right now what we are doing is we are creating a data set on our own, right? In order to do that, I'll simply open an Anaconda terminal, or you can use any Python terminal that you have. Yeah, so this is my Anaconda terminal. This has Python installed on it. So I suggest you guys to install Anaconda, or if it's a basic Python, any Python, it works. You don't need any other dependencies apart from installing Python, right? You can simply do pip install label, sorry, label img, and yeah, for me it's already installed. So it basically says the requirements are already ready. And now what I need to do is label LA label IMG. All right. Now this will open a page like this. Okay. Open directory to open a directory, and I can select. So I have all the images in this images folder. So I'm just selecting this images folder and click on select. So now what happens is I got all the images. I can go through all the images using this. Next, 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 next. I can go previous, back, all these things. Yeah, now say we are in the first folder, right? So first image is already, I mean, they're already annotated. That's fine. So there are two classes, head and helmet. In this, in this window, the important things that you have to notice is two, which is Pascal VOC, and the other one is when you click on this, you will change this to YOLO. So there are two things, YOLO and there are other one as well. Okay, the important thing is two, YOLO and the Pascal. So these are the formats of your data. I'll explain what these formats are. And yeah, edit, create a rectangle, create a bounding box. You can just click on this one. And now you are free to draw a box, whatever the box you want for your data to be. So suppose say this is helmet. I'm just drag and drop and then label this as helmet. I already have here helmet. Okay. Uh, you can. So we have a question from Arun. How do we decide on number of classes or class names? So here, while annotating the data, you need to make sure that you have the class names and all these things here ready. So let's go and delete all these things. Start from scratch. So yeah, create rectangle box. So this is a head. HEAD. Click on OK. We got a head, but this is a helmet. Again, click on this one. Helmet. OK. And this is also a helmet. Just click on this one. Whenever I do that, it would recommend here head or helmet. I can simply, if this is helmet, I can just click on helmet and then OK. Right. It'll create couple of multiples of helmets like this, but that's completely normal. Okay, if there is a head like this, you can still use your bounding box. Click on that. It's a head. Okay, so now two heads and two helmets in this picture. Simply you need to do this for at least, I would say, you need around 400 to 500 images to get the basic, real life, uh, uh, to cover all the real life scenarios, but purely depends upon your specific product. If you're doing it for object detection of medical equipment, probably you don't need so many. But people, this product is going to be deployed on in a warehouse or a railway station or something like that, right? So it's gonna see much more new images than in the training data sets. That those cases you need a huge amount of data. At least I would recommend at least 3,000 to 4,000 images if you're going that vast area. So what we have done is we have found this data set online. We have got around 2,000 images for the hats and vests. Then we went ahead and can we also use this tool for annotate, say, human poses? Yes, absolutely. You can use a similar tool, not this one. There is a similar tool for human pose estimations. Instead of drawing boxes, you just need to put the points 1, 2, 3, 4, 5, all the 17 points, 17 bones of humans. Yeah, I would definitely recommend that later on. I just don't remember the name right now, but I think it's already installed on my system. During the workshop, I'll let you know. So yeah, so when you go to the next image, it'll basically say to save them. Yes, obviously save them, and then try doing the same thing for all of these things. Helmet, and then create a rectangle box. Helmet, create a rectangle box, helmet. Okay, so now this is labeling. So
Hey,
now
Manas,
I've basically introduced, yes.
I'm just trying to clean up the questions. So how did the question, how did it decide the number of classes or class names? Was that answered?
Yes, yes, yes.
Okay, so I'm just cleaning them all up. Cool.
Super. So this is just labeling stuff, right? Now, as I said, there are a couple of formats of the data. So when you do this boxes thing, it should output some file. I mean, it should literally uh, note these 4 points and say these 4 points are helmet, these 4 points are head. It should output a file. So now that's the format that we are looking at. I'll quickly open this one and check what are the files that I created right now. Let me have a check where I created. Or yeah, let's click on save, and that should save somewhere. Let me have a check where exactly it's saved. Should usually save in the same folder. Yeah, it's there. And if I wanted to do a different one, YOLO one, save, change save directory. Oh, okay, that's the problem. So let's put the same directory as a save directory. Okay, and now I'm saving things as a YOLO format. Okay, so when I do this YOLO, put this YOLO and click on save. So this should basically save it in the images folder. Uh, so this is for the one image. I mean, hard hat worker one dot png. So which is this one, and it created a text file. If I open this text file, so these are the numbers. So 0 represents helmet, the class, and 1 represents how. So I have a few questions in the QA. So how do you start the label image? Yes. How do you assign class to each figure of the image? Images you have drawn those boxes for 3000 plus. Is this considered the best way to label training images? Yeah, I'll answer that. Yep, awesome. So the first question is, how did you start? How did you start this thing? I guess I have to restart it for that. So once you install pip install uh, label images, once you do this, once you install this, just type label images, and it'll automatically pop up a window that we are working on. This one. So the second question is, do you need to assign classes to each figure of the image? Certainly not. So yeah, here there are so many people. I'll just do it for a few, and I can leave other ones as well. And there is a problem because I got the error where okay. All right. So I think the message for this error message is because of the Python version, Python 2.7. Let me have a quick check if this label PNGs, label images supports Python 2.7. Oh, okay. So this is the label image repo. Unfortunately, it only supports 3 plus. So even on virtual environments, it supports 3 plus. So you need to have a Python 3 version, pip 3 install, or you can do something like that. But yes, it supports Python 3 version. The current version that you are using is 2.7. And the other question is, just a second, where is it? Okay, yeah. I still didn't get starting label images. Once you install pip install label images, so all right, yeah. So yeah, so starting this, you need to have a Python environment. Either it could be an Anaconda distribution, or it should be a Python 3 plus version of this environment. And you can simply install pip install image this thing and do image label img. So label img will basically open your this window. Okay, and that's for opening this part. And yes, imagine you had to draw these boxes for 3000 plus images. Yes, so for that purpose, there are some advanced techniques in deep learning. Suppose say you are developing a model for very small devices such as Raspberry Pis or mobile applications such like these. Obviously, the model that you wanted to train is a lightweight model, right? It's a very small lightweight model, and in order to train that, you need substantial amount of data. Suppose say 3000 images, right? Perfect. But you don't have 3000 images. That's the biggest problem. But there are other state-of-the-art models within the same zoo, within the same TensorFlow model zoo. One second, let me open the page. Wait, where's the page? Yeah, there are other state-of-the-art models that can do the same job with a really less amount of data. So what you can do is simply label 100 or 200 images for your specific tasks and use these state-of-the-art models to train them. So they give a really better results compared to the smaller ones like SSD mobile nets, all these ones. So use these models to train on a very small data and use these models to use, on your data set, get the predictions, use those predictions to, create more data, and then use the more data for your smaller models. People actually do that. It's a, it's a well-known trick in deep learning. People use state-of-the-art algorithms to develop more data and use that data for smaller algorithms, because end of the day, we cannot use these state-of-the-art algorithms no matter how impressive they are. We cannot deploy them on mobile phones. We need huge GPUs to run them. Basically, these models are meant to do that thing, right? And yeah, trust me, I've also done the same thing. I've trained, yeah, even I felt very tedious labeling all these stuff for more than 600-700 images. But yes, I did it for a few amount of data, and then I used the state-of-the-art model to get some predictions and use those predictions as well. That's one way of doing it. But in case if you didn't find any model, or the state-of-the-art model couldn't learn uh, uh, things better, so the only way is to label them like this, right? And the next thing is the Pascal format, Pascal VOC. So we have learned, I've shown the YOLO. I'll show them again. So yes, this is the YOLO format. I'll just type it here, YOLO. I need to use a magnifier. 1 second. So yes, so this is a YOLO format. So the first digit is always going to be the class. The class always depends upon here. If helmet is 1, it's gonna say the class is 1. If head is 0, it's gonna say head is 0. But here it's in the reverse case, because the first element that you labeled is helmet, so it became 0, and the head is 1. So when we go to this here, the rest of the 4 are the bounding boxes. So I would say this as x minimum, y minimum, x maximum, y maximum. I'll explain the concept of these things, x minimum, x maximum, in a much pictographical way, which is using a sketch pad, I guess. Just 1 second. All right. So let's draw. Suppose to say you have a big picture like this, and you have a face like this, and you're going to detect that thing, right? Now there are 4 points. So in general, each point is nothing but your XY coordinates, right? XY, and this is also an XY, XY, XY. So that means you have 2 into 4. So that's 8 points. So the model output, whatever the model that we have created for this should output 8 points. So there should be a better way to reduce predicting 8 points. It's better to predict less number of points, obviously. So to reduce that, what they have done is they have just this location, which is x minimum. So it always starts on the left top corner. So x minimum, x min is this one. This is X max, and Y minimum, Y min, and Y max. Now say if you want this point, it's just X min, Y min, and then you get this point, right? And you want, if you want this point, it's basically X max, comma, Y min. You get this point. And if you want this point, it's the opposite way, which is Y max, sorry, Y max, and sorry, yeah, you can either do it that way or I'll just do it again. X min, Y max, right? And if you want this point, it's just both max, Y max, right? Now you tried to reduce that within the 4 points. Now you might have got a question. These are in the points, right? So they actually don't represent the proper X min and Y min, right? There is also a problem called data normalization, where if this data is dependent on the image width and image height, so X min and all these things are always dependent on image dimensions, right? So in case if you want to resize your image, all your label data is lost again. You have to, if it's a pure XY coordinates, all your data is lost again. Or you need to calculate your X and Y and scale them accordingly. It's going to be a little tedious job again. So in order to avoid this, what they have done is instead of storing XY properly, I mean like this, just divide them by your height. So divide your X by I guess your X by width. So if this is your X divided with your width of the image, if this is your Y divided with your height of the image, and that will give you ratios like this. Like, yeah, these are all the ratios. Can you share a link to download the application that you're using? Cannot figure out if I'm downloading the label box or something else. Do we need to assign class to each figure of the image? So yeah, the second question is basically, yeah, you definitely don't need to assign every image. I mean every picture. I mean every object within the picture. You can just do few, 4 or 5, and then leave the rest. Okay. For the object detection app, sorry, I didn't get that part. What is the object detection app? And I think I've answered the 3000 plus images question. And can you share a link to download what you have open right now? Oh, this one, this application. So this application is nothing but it's a Python package. You can install it using pip install label image, and then open it using label img. Okay. Yeah, in case if you have doubts on this one, you can contact either Anson, Christy, Ashit. Basically, they can help you install this on your machine. Label images. You can contact Christy and Anson, Ashit. So you can find them on the images, on the smaller images there, icons. Yeah, to install this one, right? We have discussed the YOLO format, as I told you, this one. And now we'll go and see what's the other format, which is the Pascal, this format. Okay. Yep. This format, right? I'm saving the same thing. I'm not changing anything. I'm saving it. If I save it using a Pascal format, let me see what's the output is. Okay, 1 second. So this is the text format which I showed you guys before. This one, closing it. This is the XML format. So if I double click on that, the XML files are going to be uh, open on a website like this, on a local thing, because it's an XML format. So this XML format has its I'll just increase the size. It's extremely hard for you guys to look at. Yeah, super. So this XML format has its own advantages, and TensorFlow supports only these XML formats for the models. So the path contains the path to an image, right? The file name is just the name of the image, which is nothing but this one, and it contains the parent directory, which is the images, right? And the size. The size is nothing but the size of your image, right? And objects. So the objects are basically the number of objects that you created, the bounding boxes, I would say. So you can minimize them like this. Yep. So we created 3 boxes. You can see it directly in here. So we have 3 boxes, 3 helmets, 3 helmets. We can see the same thing. We have 3 objects. So the object name is helmet. The bounding box is this one. So as I told you, the Pascal format is going to have the exact points, the exact XY points, instead of I mean X minimum and X maximum points, instead of having ratios, because the image dimensions already included in the data. So yeah, for some reason it doesn't accept the ratios as the text format, right? Similarly, the same thing, and this is for the same thing. So I'll just close this file. I'll add it. Okay, it's not responding. Just give me a second. Yep, let me close this. Let me open it again. So I'm again opening an Anaconda terminal here. Yep, just give me 1 second. This should work. Yep. So this is an Anaconda terminal again. I'm opening the image. So the label image. LABELIMG. Click enter, and that will open my label image folder. Again, open directory. I'll just go ahead and click on images. Now we have this. I'll go to the next one. Yeah, the one which we are working on is this. So we just have 3 objects here. All the 3 objects are helmet. We are doing the Pascal format. Yes. And now I want to see the save. Change that. We'll just keep this as images as well. We are putting the save directory same as the images directory, so that we can see the files within that same directory. Now I want to draw a box. Suppose, say, I just draw this one as head, right? Even though it's not a head, I'm just drawing it for seeing the format, how exactly the format is. So now there's a different class called head, and I'm saving it. I just saved it, and let me return to my images folder. So this images folder has this file again. I'm just double clicking on this one, and it opened this file. Now this file should have 4 objects. You can see the head object here, the name head, and then the warning boxes. All right, perfect. So similarly, you
Okay, I'm not sure. It looks like Manas disappeared. Maybe he forgot to leave his. It looks like a classic example of maybe he forgot to charge or attach his charger to his computer. Okay, let's see what happened. All right, well, we do that. So 7:28. Oh,
can you guys?
yeah. Did you forget to charge your laptop or what?
No. This Remo is basically not responding for some reason.
Okay.
Is it too long, or where exactly did I miss you guys?
No, we
I
just
was not
lost you for the
concentrating on
last
this.
1 minute.
Oh, last 1 minute?
Yeah. So let's not use the Q&A for the spamming. Whoever the writer is.
Yes.
Yeah. So we use the chat for spamming, the Q&A for the Q&A. All right. So we had on the other side, we have Morgan who had an issue. You want to look in the chat? Pip install. Pip is not recognized. I said, oh, that's on your side, I think.
Yes. So it's right now we are using a general command prompt, but you have to use a Python command prompt. So you have to install Python on your laptop or an Anaconda distribution. Then the pip command works.
Yeah, right? I think that's the reason why we're using what's it called? That's why we're using Colab, right? Because this way they don't have to install it on their system.
No, this thing we have to do it on our systems itself.
Okay.
Yeah, so it's just basic Python installation, and then we can jump onto our terminals.
Okay. Yep. So okay, I'll leave it back to you.
Yes. So I'll just type that thing again. Yeah. It's image. Yeah, that's the one. Open that software, and so I think, did you guys see
You're not
this?
sharing your screen anymore.
Did you guys follow through the different formats of labeling? Install pip. Yep. Awesome. So for this project, we'll be using the XML format. However, I've included the scripts in case if suppose you find a data set online in Kaggle which has TXT format, and you want to convert it into XML format to use object detection. I will still I already put all these things in a Google Colab repo. So our project repo, and also explain you guys how we can use them later on, right? But at this point, obviously, I'm not gonna sit and annotate all these things because it's a really tedious process. So let's quickly jump onto our Colab notebook. Where's a Colab notebook? Yes. Oh, we have to reconnect this. Okay, probably install them again. But yeah, let me see. I have to install them again. Shouldn't take much time. There, it's done. So if this thing happens again with you guys, I mean, if your virtual environment crashes or you need to redo it again, you don't have to clone these repos again, because they're all saved in the drive, right? You can still have your drive open and still have all your files, all your models, research, TensorFlow, everything within this, right? All you have to do is install TensorFlow. Just click on this one and it will install the TensorFlow for you. The very few things that you need to do before, I mean, for the initial, the second setup, the first setup is obviously it's gonna, you have to follow all the steps. But the second one, it's very quick. You can install TensorFlow and then simply open this. Just a second. Let's wait until this is done. Yes, that's done. Let's just restart as well, because awesome, it's restarted. Just run it again. That's done. Now let's go to the working directory here, the clone. So this cloning, you don't have to do any cloning. So git clone, you don't have to do that because it's already cloned. You have all the data here. But let's just execute all the files, all the rest of the things. We have to install this protobuf because you're installing this object detection in your Python environment, right? We have to do this, and it shouldn't take time. That's done. Again, we are not cloning this again. Just go to the folder and click on make. You're just building it. That's done. And again, we are copying this one. That's done. Let's go to the research folder. Copy this setup file. I think it's already copied, but you can do it again. Just install this. So once this is done, we can quickly jump onto our data preparation part. Sometimes installing TensorFlow, I mean, installing this API will take a really long time because uh, it wouldn't get all the packages. I mean, packages are sometimes headache. So that way you can just stop them and again restart them, just like this. Make sure the runtime is properly set. Yes. So while this is happening, you guys have any questions so far? You guys can put something like a hand or an emoji, like that, and I will enable you guys to basically speak, and you guys can speak and ask questions. Just you can put it in the chat and I guess Emily wants to speak. Is it? 1 second.
Yeah, I invited Emily on stage. So Emily, if you just go into the, if you
Yeah.
open your cam, you should be able to speak freely. Okay, well, she's not. Let's check the chat.
That's okay. That's
I
okay.
got so Welia's got a question in the Q&A. I got an error when executing Python object detection. Just maybe have. Okay, let's go with the first one. If the Google Colab is used as an environment, then the hard-coded image path in Pascal file.
Yes. So what I'll do for this one, so here I created a folder which is images underscore annotations. So this folder will have your image, which is .png, and your XML format. So when you click on this one, you can either download them or like this and just view it online like this. So you can just dump them all in one folder. Instead of this, you can easily use Google Drive for that. So image annotations, you can simply put all your images and annotations within the drive. So the repo, the Launchpad, the workshop repo already has 50 images of, it's a sample of 50 images labeled, everything done within one.
Sorry, my bad. I pressed the wrong button. Manas, do you want to come back up?
Yes. Can you guys hear me now? So yeah, for I basically put all the sample images in the 50 images in the image/annotation folder. So you can work with this 50 images for now for demonstration purpose, but later you can dump all your images, 2,000-3,000 images just here, and then it should work. It should work. And yeah, I'm not sure why this is taking a lot of time. It's okay. Let's see what we can do. Or let me restart one time, because it's definitely taking a lot of time. Okay, to the drive, this. Let's do this. It's already installed 2.3. Let's do this. Time, install these, and then do these as well. Yeah, this time it's much faster. It totally depends on your the environment. So we have a request. Leave this request. 1 second. How can I leave this again? I think you forgot to share this.
Yeah, but we're not sharing the screen.
Oh my God. I couldn't see the red frame. So usually if I share a screen, I see a red frame, but this software, I couldn't see that thing.
Yeah, all right. Lucky we started early, so we are still on time.
Oh, is it? Okay, awesome. So yeah, I just installed this one, so it's done. I don't want to test it because I know almost all the packages are right. So we can skip this testing part. Let's go to this data preparation. So in the data preparation, let's make sure we are in the working directory because CV1 workshop is our working directory. So the TensorFlow is going to accept a format called TF records. So I'll explain what this TF records are. Uh, Now, at the moment, you have data in this format, right? There are a bunch of images and the XML format. Now, you need to convert these into TF records. In order to convert them into TF records, we need a script, a Python script. So this script is nothing but it's a it's a TensorFlow script. I've included them within this the repo itself. So while you're cloning them, you should definitely have all the scripts here ready. And we are executing this XML to tfrecords.py. So from this point of time, it kind of gets complicated, I would say. So let's just open this one. So all the py files, you can just double click on them and open it on the right side. So now you see there are arguments. So so these files, almost all these files have arguments like these. So these arguments are basically the paths that you want to paste. Just increase one more size. Can you guys read it now? Yeah. So yeah, the first one is the XML directory. So this path, it's asking the XML directory, which is the same one because we have everything in the same directory. So which is images underscore annotations. So I just placed my directory name here, right? And let me see the second one, the labels path. Now the labels path is this. Now there is a question. We have XML file. We know that this bounding box is head and the other bounding box is helmet. But the model cannot understand uh, the literal literal word, right? It cannot understand what helmet means and what head means. So it has to be one hot encoded. Something like head is 0, the other one is 1. Just like the text format. Unfortunately, as I told you, the TensorFlow API doesn't allow the text format, right? Text format is for YOLO detection. So this XML format also need one file called labels underscore pbtxt. So this is a folder that I have. I've created this classes underscore labels underscore dot pbtxt file. If I open this file is just like a JSON dictionary. So just JSON string uh, has items. So items are nothing but your classes. So if you have one item which is head, the name is head, the ID is 1, and the display name is also head. So this way you can, if you have 4 classes, you can simply copy, space them, give a different number, 1, 2, 3, 4, different number, different class names, and you're good to go. So these are all the class names that you have to save. Even if suppose say your data set have so many classes, 90 or 100 classes, something like that, then you need only two classes. So you have Coco dataset. As I told you, Coco dataset has like 120 classes. But suppose say you only have you only need 10 classes, aeroplane, some very specific classes for your object detection. You can filter them out. You can simply filter them out here. So for Coco dataset, you can see here 90 classes, 90 items mentioned. You can delete all them, just put 10, whatever the classes you want here. Just right now we are just doing with two classes. So I put only two here, and you have to filter them in the script as well. So I'll tell you where exactly we can filter them. So when we go to this XML to TF records here, oh, sorry. So here we attach the pb.txt here, which is the labels, and the second is the output path. So now output path is basically a folder where you are saving this TF records. So here I don't have any folder right now. TF records, I don't have any folder right now. So what I'm doing is I'm again creating a folder using this command, basic mkdir. We'll make sure we are in the CV1 workshop folder. Execute it. So that means we are in the CV1 workshop folder. Now we'll create a TF records, which is this. If I refresh it, it should create TF records folder here, which is empty. Now I can use this folder TF records and give it a file name. It could be train underscore records or train underscore hat detection, something like that. Hat detection or anything like that, right? You can put a name here, but I think, yes. So I'll just rename it. I'll put it this way, and then save it, Control S, and you'll get remove that star mark. So if you have a star mark here, that means you haven't saved the document yet. So just make sure that you save the document, and yeah, just run. So yeah, similarly, you give the images here, images folder, which is the same folder which has the XML files, is the same folder, and it's a it's also creating a CSV. I'll tell you why this CSV is really important for us later on, right? Uh, so there are 50 images. So it's starts with one. I think there are 51. That's fine. So yeah, it's now says we successfully done this thing, and we could see that in the TF records. So in the TF records, we will see that we created this TF record file. Now, once we created this TF records, we don't need these images and XMLs. We are not dealing with images and XMLs again. It's just this one, just this file. This file has all the images and all the annotations, everything in one file, right? We compress the entire data to this one TF records. It's just like a database that has everything in it. Okay. And you can simply delete this. In fact, you can completely delete all these images and free up your drive as well once you create this dot records file, right? And now the data is done. If you want an evaluation data set, suppose this is your training data set. Now you want evaluation data set. It's the same process. You do it again. That's it. You create a different folder put all your evaluation images, like 10% images, or suppose at 10 or 15 images, put them in that folder, change the paths, and simply create a different TF records. Just put, instead of train, you put test. Instead of train, you put test, and that becomes a evaluation data set, right? It's the same way. But at the moment, we don't have any evaluation data sets, because doing evaluation on Google Colab uh, is not possible for this API. Unfortunately, that's because uh, this API will work. The evaluation works like this. You have to run two different programs at the same time for evaluation. But unfortunately, this Google Colab will not allow us. Because we are only going to run one cell at a time. Once one cell is executed, it will go to the next one. So it will not. I mean, we cannot do a parallel processing on Google Colab. So that's still fine. We can still monitor all the trainings, losses, everything in detail. And I'll explain this virtual file.csv. So it also created a CSV. I'll open the CSV. So this CSV is nothing but for our reference. So it's the name of the image, height, width, height, the class of the image, and then the four values: x minimum, y minimum, x maximum, and y maximum. They're all in pixel values. They're not ratios. They're all in pixel values. That means they're already multiplied by the height and width. Yeah. So it'll just generate these files just for your reference. Okay, that's done. Now let's go. Yeah. Now all we have to do is select a pre-trained model from the model zoo. So we'll open the model zoo. Now we have so many models here to select from. As I told you, just you can take a calculator. Uh, it is always like a balance between the accuracy and the speed. So if you want a very accurate model, you can still have it. You can still have literally the best models, but it depends. It really depends upon what hardware are you using, and how do you I mean, want to deploy this in future. So it all depends upon many aspects. So at the moment, because Google Colab is a really lightweight environment, we'll go ahead with a very simple basic model, which is SSD MobileNet V1. It's 48, so that means let's calculate it. So that's 1000 by 48. It's 20. So it's going to give us 20 FPS if we use this. 20 frames per second. It's still fine. It may not be real time, but still fine. So if we used YOLO, so we have a question. 1 second. So if we used YOLO that uses the ratio rather than the actual XY values, would our CSV have? All right. So the problem is we cannot use the text file, I mean TXT format for object detection, for TensorFlow object detection. TXT format is for YOLO. I mean, YOLO is very similar to object detection API, but uses a different architecture. I mean, if it's from a different company and a different architecture, it uses different things. But the process is same. I just gave a brief explanation of the different formats because people might have created data sets in TXT format, but we should be still able to use them with object detection, right? So we need something which can convert TXT file format to XML file format. So I have scripts for them. So here you can see convert txt to XML. So if I open this, so this will basically take input of two inputs. So it will take images as an input, and this is a second, I mean, destination directory. Okay, this is a destination directory. So this could be a blank empty directory where you have where you need where you can save all your XML files. You give txt files as input, you get XML files as output, right? And all this code is uh, basically going through all your txt formats, resizing them, multiplying them by your height with all these ratios, and giving you the right format, exactly same as the XML format, right? And previous YOLO. Yeah, I think I've answered that.
Yeah, the question came from Kali. I was just putting it on
Yes,
the slide.
yes. So I think I've answered that question. We can, yeah, we'll definitely go through this once. If we have a a data set which has which is in txt format, we'll use this script to convert them. In case if you guys find a data set really useful, but it's in txt format, you can definitely come back to me and we'll implement this script and convert them to XML format, and then continue our work. Yeah, sure. So that's there. And the other one is, yeah, let's go ahead and download the models. So to download the models, I'm just creating one folder, which is pre-trained models within my working directory. I'll create a pre-trained models. I can see it here, pre-trained models. And this is the link to download a specific model. To get this link, you have to go to the model zoo, just copy it, right click, copy link address, and go back to your this thing. You can simply just paste it though. Yeah, it's the same link. You can simply paste it like that. wget is a command to download things on Linux. So you can use this command to download any link, given that the link should end with a file format. So .tar is a compressed file format. .png is an image file format. .jpg, something like that. But the end file should be a file. It should not end up just like a website like this. So in the Colab on the top, you can see something like this, right? So this is not a file. So we cannot use this here to download this entire Colab. So it should be a file. And that's done. I'll just, so right now we are in the pre-trained models. This is the current working directory, pre-trained models, and then I'm downloading this. Yes, that's downloaded. So when you do ls, it will list out all the files that are in that particular directory. Unfortunately, I think I've downloaded it in the, yeah, I think I've downloaded it outside, outside the pre-trained model. Let's just run this thing. Now we are inside the pre-trained models. Let's just download it again. Okay, if I now do ls, I'll just have one file because right now I'm inside that folder, right? Perfect. Now I'm extracting this because it's a tar file. It's just like zip, zip file. For this model, it's a tar file. It's a different compression technique. In fact, you can untar it. They say untar it, though, so it's just unzipping it. You can do that. Now we are extracted our model. This is how our fully built model looks like. So it will have three main files. One is checkpoint folder. The second one is saved underscore model, and the third one is pipeline.config. Okay, there are three files. For every model, there are three files. Checkpoint files, these files are the training files, right? When you do a model training, for suppose you set for every 10 epochs, I want to save a checkpoint. This is what the checkpoint is. And usually when you download a model from the TensorFlow model zoo, this is your best checkpoint. So they would find which is the best checkpoint, and they would obviously put that best checkpoint here. And the second one is the saved underscore model. So underscore model will usually have three files in it. Again, one is variables. So these variables have all the necessary data all combined in it. And there will be also one more folder, which is assets. I'm not sure why this particular model doesn't have assets, but few other models will have assets. And most importantly, saved model.pb. PB is a protocol buffer. Can anyone paste me a link to that object detection tar file? Yeah, sure. 1 second. You can just right click on this one, copy the link. You can just paste it here. So yes. So there are two. What we need to concentrate here is two important files. One is saved underscore model.pb, and the second file is pipeline.config. This is a configuration file that we need to edit for further training, but saved model.pb is a fully built model that you can use for inference. Suppose, say, you want to use this model itself directly without any training. You simply need this file, nothing else. You need, I mean, this saved model folder. That's it. Once you have this, that will work on all the 90 classes of Coco Coco dataset. Basically, this model is trained on Coco dataset. So if you use the saved model, it will work for that particular dataset. And it has 90 classes to classify. And it's already a perfect model, already built model, right? And awesome. So we have downloaded the model. The second part is, uh, I think we'll have a break and then continue this model training. Before that, what I'll do, I'll just recap until this model training, right? Because from model training, it's going to be little, I would say, uh, coding stuff. I mean, you have to do so many modifications in the script so that uh, you have to get really good accuracy as well at the end of the day. So I'll also give you tips on how to get a good accuracy if you have very less data to work with, and what are the parameters that you have to care while training your model, all these things. Uh, so yeah, model training we'll do in the next half. And yeah, any doubts, any questions so far? Alicia, you're muted.
Yes, we have one question. How do you open the script on the side?
Double click on that file and it will open on the right side.
There you go. Easy done. Okay, so I think what we can do is we can take a break. So feel free to use this time to start thinking also about what you may want to do.
Yeah.
I have downloaded Python, but pip is still not working. So just for your own knowledge, Python is not one of those things that, I mean, sometimes it creates issues.
Yes.
Um, so you might need to do things such as installing the, what's it called? Installing the, put it in your path, set the environment, restart your machine, and magically will work. Yeah, it's not like installing, a game on Steam or installing Office. Yeah, unfortunately, it may need a few a few trials. Um, but anyway, so that's part of doing this as well. The difference between doing this workshop today and doing something on Udemy is the fact that we are here to actually answer all the questions.
Yeah, yeah,
Otherwise, trust me, I'm pretty sure that there are much better people at presenting this kind of stuff than me and Manas. We do it because we like it, but we haven't really prepared every single word or scripted everything.
yeah. It's
But the advantage is
completely
that we're here.
random. Yeah,
So, but when I double click it, it download the files to my PC. Oh, it could it be the browser? What browser
uh
are you using?
it would, for XML files, it will directly download it
Okay.
to your things, but rest of all the files you can open it on the right side. Just I think only the py files, .py Python files, you can open on the right side. And yeah, XML files, you might, I mean, download them locally, because we cannot view XML files on the web.
So also what we want to do when we come back is
Yeah,
perhaps we actually give people like a 1 minute to introduce themselves. So we are gonna do a bit of an icebreaker. So let's
yeah,
have
yeah,
that camera on. Perhaps do something like 20, 30 seconds you introduce yourself, and 30 seconds the kind of ideas or the kind of solutions or problems that you want to work on. Um, I mean, if we were in person, this would have been much easier because I would have just pushed you into the middle.
yeah,
But being here, a little bit more difficult. Um, so anyway, let's do that. We'll catch back with you at 1 o'clock.
yeah,
And any other kind of problem, perhaps maybe you can try to ask Manas or ask in the chat, see if there is something that we can do about it.
yeah. Any questions? I'll be on the chat. I'll be in one of the rooms. You guys can ping me, no problem.
Yeah.
Yeah.
All right, guys. So I'm gonna stop presentation, and I'll see you guys back at 1. Bye
Yeah,
bye.
sure. Bye. Hi, everyone. So let's start the second part of our workshop, which comprises more of model training. In We build these models to for production environment. I'll just share my screen.
Yeah, and I also wanted to mention, so don't worry too much if you fall behind. We understand today there could be quite a lot for people who are not ready to digest. Um, so yeah, don't worry. That's why we set up the whole week. Um, Probably what we would like to do is maybe at the end of the day we have some time to go and try to help you tonight. But after that, we also have tomorrow morning. So we have set up some sessions. If you have some trouble installing things, we can try to help you. It's not a problem. So, yeah. So let's just move on and enjoy, and let's start doing I guess, one of the hard parts this time.
Yeah. So yeah, back to the same notebook that we were working on before. So since the session has been restarted, we need to again initialize our environment with all the packages. So I'm just doing the same thing, running almost all the cells without the clone command. So the drive folder already has all the files and folders that we need, so we don't have to clone them from anywhere else. So yeah, just installing, going through the installation of proto files and then building it. It's done. These files, it's done. Yep. And copied. Yep. Let's just wait for a few minutes for this installation. So yeah, in the morning session, we learned until the data pre-processing part. So the data pre-processing is nothing but converting all your images to your TensorFlow record. So you have image. So initially you have images, and you label them, or if you already have a labeled data set, you just put it, or put all them in one folder and run scripts accordingly that can convert this yeah, especially this one. It would convert all these images and XML files to TF records. If you're a bit curious what exactly this script does, definitely have a look over here, and you will get an idea, I mean, fair idea on how this is done. So yeah, as I said, in case if your data set has many classes, suppose say 90 classes, but you just want only 10 classes, you can edit them here in the class declaration here. And also you have to filter them in the TF records. So before creating TF records, what you have to do is, uh, this is the place where you need to specify which files you want, right? So I'll give a small example. So this will iterate through the entire objects in the data set. So suppose you have 1,000 objects, it would iterate 1,000 times. The entire two loops would iterate 1,000 times, and basically say it would get the bounding boxes of. So there are 4 bounding boxes for each object, and there is a class name for each object, which is .text, and there is size. Size is height. I mean, one is the width and one is the height. So these are all the I mean, the numerical values of one object, right? If you have 1,000 objects, this would iterate for 1,000 times. So what you have to do here is use the component member, because a member is one object, because it's object here, and you can simply filter it using if loop, or you can pass an entire string. Suppose say you want 10 classes, you can simply put all 10 classes in your array like this. Say uh, tiger, something like this, or any class names like this, and give it a name. So now this is a list of strings, right? So as it's a list of strings, what you can do is simply, if member is in list of strings, then only do the entire thing. Else just skip it. So that's how you filter classes if you want a very specific class in a very large data set. It's a bit of Python programming, and you can still, I mean, easily you can filter them. Yeah. For now, we can just leave it like that. Let's go and check if it's installed. All right, so this is installed. Now we can start training our models, right? So we have downloaded a pre-trained model, which is SSD MobileNet V1, and we have extracted them as well using the tar function. And you can see this downloaded model over here. And I've also gone through the basics of what these file formats are, what pipeline does, and what saved underscore model does. We'll mainly concentrate on pipeline.config for the training part, right? And when you click on this one, double click on this one and open the pipeline.config, this is your config part for your model. So this pipeline.config will have every hyperparameter that requires for your training, right? You have to specify number of classes. This is an important part. So I request you guys to basically make a note on what are all the things that you need to change on this pipeline.config, because there few things are really important to change. So you need to know which things are really important to change. So one is the number of classes. So number of classes 90 because it's trained on Coco dataset, but we are going to change this to 2 because we just have 2 classes, right? And this is a fixed shape sizer. Uh, for now, you can ignore it, but what happens is if your image is of just give me 1 second. I think we have a question. Can we use object detection API for just classification? In that case, can we do? Yeah, I'll explain that in a bit. We'll actually go through that now. So this fixed shape resizer is nothing but a kind of data augmentation technique. It would try to resize your image to this size. So what would happen is, suppose this is a square, right? So it has equal dimension, 1:1 ratio. Suppose say you have a 16:9 ratio image, which is much wider, right? It will still try to fit the width. So the width, it's going to scale based on the width, but the height is going to be uh, still in terms of 16:9, right? It wouldn't, I mean, expand the height. It would still keep the aspect ratio 16:9, but the width is going to be 640 pixels. And yeah, this is a mobile net, SSD mobile net. We don't have to change all these things. If you're statistical, if you know what these layers does, what bash normalization layer does, and what ReLU, all these activation layer does in detail, then you can definitely go and tweak all these decays, epsilon values, all these things. But yeah, if you want the standard model, you completely ignore all these values and use them until yeah, I'll basically go through here. So we have so many batch normalization layers within this SSD architecture, right? Now we have an option to specify uh, which batch normal. Suppose the ReLU 6, the 6 would represent maybe the sixth batch normalization layer within the mobile net architecture. So for that particular layer, you can edit these values, right? It's pretty much customizable. You can still copy this, and then if you know that there is a ReLU 7 and you want to change for that, you can still change for that in case if it is in the model. But if it is not in the model, it would definitely give you an error. But that's how you paint stuff like for hyperparameter tuning. And yeah, these are more advanced. Mm. So usually object detection models contain different segments in them. I'll try to draw them and explain it to you. Suppose say you're passing an image, right? You're passing an image and you want some output. So your expected output is something like this. Four values, these four values is your expected output, four values, and the class for each four values. So four values will have one class. Either it's a helmet or a head or some other any class like this. So this class would represent in one value. So that's five values in total, right? So this is your model output. To get this one, it's a classification task. To get these four values, it's a regularization or a regression. I would say regression task to get the four values out of it. As you know, MobileNet obviously is a encoder. So encoders are usually drawn like this, like a bottleneck. You might have you might have seen many images like this, like a bottlenecks like this. So these are nothing but convolutional operations on them, and they would have batch normalization layers in between, activation, ReLU, something like in between. But the end of the encoder will be a small latent space, which is a fixed latent space. So the entire image is converted to a small latent space. So we call this process as feature extraction, right? This feature extraction is nothing but your feature extraction layer. This entire block is called your feature extraction thing. So if you have activation layers, if you have regularization layers, you can change these weights within your feature extraction. Okay, the next goes is your the box prediction, the four values that I told. So the four values is again a different network, connected network to your feature encoder. So this is where you can change all these other values. You can change your kernel size. You can change your depth. Depth is nothing but, suppose in here, the size of this is basically say 5,5,256 something. This number, and this is your batch size. Suppose 8 is your batch size. This is your depth, and this value is definitely going to create a significant impact on number of parameters that you're learning. If this value is much higher, it requires a lot of parameters to learn. So yeah, we got a question: how do we determine reasonable values when tuning the hyperparameters? That's where all the state-of-the-art models come into the picture. When we develop our own model from scratch, then you need tools like TensorBoard, weights and biases, all these data distribution uh, visualization tools to actually check how the data is distributed uh, in each layer. And you need some statistical knowledge to also check if that's the proper way or not. And that's how they tune it. It's a really statistical process in deep learning. For this workshop, I would say it's definitely, it's a very, very long topic, maybe a PhD topic to design a network like a SSD. So we would simply rely on the state-of-the-art techniques and their already fine-tuned models, because we know that they're already good. So just use them. That's it, I would say. But if you want to experiment, I'm just giving you a way that you can change them, where exactly you can change them. I'm just telling you where you can find stuff, right? And yeah, there is some post processing as well. It's fine. Yes, and here comes your loss function. So loss function, as you know, in deep learning or any machine learning, loss function is the most important part, right? It's also known as cost function. That's how the model back propagates the error from the to the entire network and change its weights for each layer, right? Here, for SSD mobile net, you can see they have used weighted sigmoid focal loss, which takes two parameters as its values, gamma 2.0 and alpha, something like that. It's a classification loss, and you have a different loss, which is localization loss. Localization loss is nothing but your regression loss, which predicts 4 values. Classification loss, I would say, similar to your softmax and categorical cross entropy or binary cross entropy. Because it's similar, it's not the same, completely different things, but it's similar. What it does is it gives a probability between two or more classes. So the output of your classification loss is always going to be your probability, but the output of your localization loss can be numbers. Yeah, it's always numbers. It could be any number, any pixel values, or depends upon your problem. At the moment, it's just the pixel values, the 4 pixel values that we are looking at. Xmin, Xmax, all those 4 values, right? And here's you can specify the weights as well. I will explain this weights while we are training. So weights is nothing but you're basically saying treat both the losses equally, 1:1 ratio. But if your model is very weak at classifying things, you can increase the weight for this one as 2 and this one as 1. That means you are giving more priority to your classification loss than your localization loss. You can change those weights here. And this is your training config, right? So this training config file is responsible for your training parameters. So in general, when you're doing machine learning or scikit-learn, anything like this, when you do .fit and then you specify all the things, right? You specify your learning rate, you specify your cosine decay in case if you use it. You also specify your batch size, step count, all these things. So all these things are specified within the training config here. I'm just going to go with batch size 8. That's purely because the Colab supports, it might crash if we go higher batch sizes because the GPU and the CPUs are not that great. So batch size is nothing but this. So this is one image, right? Batch size is nothing but if you specify batch size 8, that means you are passing 8 images at a time, 8 images. That means you have 8 images and you want output to also have these things for 8 images at a time, right? So the input shape is going to look like this. 640, 640, comma 3. 8 is your batch size, height, width. This is your channels. Channels are nothing but RGB, red, red, green, and blue, because images are always 3 channels: RGB, red, blue, red, green, blue, or it could be BGR as well. Sometimes it's BGR. We have a chat. So is there any rule on how to decide what the batch size should be? Yes, awesome. So how to find the perfect batch size for your training? The batch size is also a hyperparameter, and you need to know which batch size fits properly for your training, right? I would give a small tip for it. Uh, so batch size first depends upon your hardware. First thing, hardware. This whatever the amount of memory and your model will always have number of parameters in it. So if suppose say your model has around 43 million parameters, this image of batch 8 images with 43 million parameters, it should fit in your 12 GB of GPU. 100% it should, 100% it won't fit. That in that case, you either need to decrease your model to a very small light model, and suppose say of 10 million parameters, and use batch size 8 or 16, or you need to have a proper balance of that. That's one part. Suppose say you completely eliminated the problem of having hardware problems. You have like 10 GPUs, and you need to not, you can basically go even batch sizes, higher batch sizes like 128, something like that, right? In that case, the problem comes is your data set. Now say your data set is just over 1,000 images, right? Your data set is just 1,000 images, and you're using batch size of around 128, which is a very, very large batch size for computer vision problems. Not for scikit-learn, not for machine learning, but computer vision problems, 128 is a really big batch size. So now what happens is, one epoch is nothing but going through the entire 1,000 images once. So that means 128 images at a time. So one step, you go 180 images, or 128 images. Second, you go the double. Third, until you reach 1,000. After you reach 1,000, you go back to the first one. And this cycle is one epoch. That means if you're training your model for 30 epochs, obviously you're gonna rotate for 30 times, right? 30 times. Now say you have 128 images, and you're shuffling them continuously for 30 times. There is a huge chance of overfitting, or learning the obvious weights. So what would happen is, say there's many dog images, and you're trying to classify dogs, horses, and humans, and 80% of your data set is dog images. So this higher batch sizes with many repetitions, what it will do is, it will focus more on classifying dog images 100% right, leaving the low classes behind. So it will only train the obvious ones, but it will leave the rest of the ones which has very less weights of classes. It will leave those things. That's again a class imbalance problem. You have to decrease the batch size, uh, or decrease the learning rate. Then if you're using this batch size, you might need to go a really low learning rate like this, so that you slowly try to learn them for a higher epoch. Then yeah, obviously if there is a low learning rate, you might need to train it for a bit more. It's all I would say is kind of a balance that you need to think of: your hardware, your data set, and your training results. It's balance between this three things. So usually when you run for one training process, and the next training process, if you try 8, batch size 8, and directly jump to batch size 32, if you don't have a problem of hardware, then you will quickly know what's your loss, how is your loss is affecting with this jump, with this quick jump. Then you'll understand, okay, going higher will obviously is a problem for me in this particular case. Then obviously no, but for some cases going higher can be good. Yeah, some specific problems like face recognition, uh, people use higher batch sizes, so that especially when it comes to batch normalization, it considers a 32 or a 64 images and put them all in one distribution, and then it can easily figure out which person is like, because they're all in one proper distribution. So they can easily be segmented within that distribution, easily find and can easily find which person is who. It depends upon problem to problem, but for current object detection problem, lower batch sizes are always better. And all the other the state of the art models, they're either 16 or 8. That's like a small introduction of how we use batch sizes. So I'm changing the batch size to 8 just because we have hardware limitation. And let's go to the learning rate. Here is our learning rate. At the moment, I'm just leaving it like this, but learning rate is always depends upon your data set. How is your data distributed? But at this moment, I will not ask you guys to know how your image data is distributed, because that's a really big task of a data scientist to know the data properly from end to end, how all the images are, how it is distributed, and how all the classes are distributed. So for now, you can just leave them like this. During our training, during our training and during this week, based on your data and based on your problem, uh, I can suggest you guys to, what learning rate would be better. I'll suggest that based on your problem, right? And there's something called warm-up learning rate. It's a technique we use in transfer learning, because what happens is when we are using a fine-tuned models, right? So say we are using MobileNet. So we are using MobileNet. So this is trained on Coco. So that means the entire the encoder part is well trained on Coco dataset, right? So here, warm-up learning rates are always higher. A little higher. Sometimes, no, sorry, they're always lower. In fact, I would say. One second. Why is this? Oh yeah. So there always starts with a very low value, and the graph you can see is something like this. Yeah, they will always start with a low value and increase the learning rate. That's because you don't want the initial layers the initial first iterations, so second iterations or third iterations, you don't want the model to learn much information at that time. That's because if you start the model to learn at very high learning rate, it would forget the weights that we have trained on. So we don't want to forget these weights that easily. So we want the influence of these weights in our model, and then gradually learn the new things. So I think learning rate, warm-up learning rate is a really good thing. So I want you guys to basically go and check what the cosine decay learning rate is and what warm-up learning rate is. You can simply go here and find it on some images like this. Yeah, different cosine learning rate, cosine decay learning rate. There will be sine decay. There are different learning rates. It's basically the curve, how the curve is represented, some statistical way, and some specific problems need specific uh, type of learning rate in computer vision. But for object detection, it's whatever the model that you're using right now. That's it. The important part here is fine-tune checkpoint. So here you are asking the checkpoints of your pre-trained model. We can find it here. So this is your pre-trained model. You have downloaded SSD MobileNet here, and inside the checkpoints, you would find checkpoint.0.data. So this .data is the file that you want to paste over here. And unfortunately, this got. Let me have a check. Oh yeah, it's done. Just a second, guys. Oh, not that one. Yeah. So this is two. They're all saved in the drive, luckily, so we don't have to edit them again. Batch size 8. We'll leave them constantly. Yep. So fine-tune checkpoint here. So we'll go ahead and place our checkpoints, which is pre-trained checkpoint. Just using this. Yeah. Control copy path. So there is like 3 dots here. You can click on that and then click on copy path, and you can place it here. Control V. It's a very big, the path is big. However, what you can do is, if you specify the slash in the front, what it will do is, in Linux, it will go to your root directory. That means your first parent directory. And from that directory, it will try to root from one folder to one folder to one folder. But right now, we know that we are already on our project folder, right? So you can just delete this. But make sure, if you are using from the current folder, make sure there is no slash. Okay, there shouldn't be any slash. If you put slash, that means it'll go back to the root directory and try to search for pre-trained models, and it wouldn't find pre-trained models in the root directory. So it's this. And also remove this .data extension for the checkpoint. Just clear that thing. It's just until the 0. We shouldn't put checkpoint on -0 .data, because we need the checkpoints. It's an entire thing. It's just not this particular file. It's the entire checkpoint of 0. And Yes, that is the checkpoint. Checkpoint of 0 is the actual name of it. Okay. And we specified the checkpoint. You can specify the number of steps. So number of steps is again depends upon your data and the batch size. Uh, yeah, I can. Yeah, we can actually skip that, and I can tell that later on because we're anyways dealing with just 50 images. So here, fine tune checkpoint type. So this fine tune checkpoint type, as Arun has asked, can we use this object detection API for classification purpose, image classification, cats or dogs or something like this? Yes, we can, 100%. And that doesn't need XML files, and it only takes images as input. But the second, I mean, the label is going to be 1 or 0. So instead of in the XML, you have objects, right? Objects and bounding boxes. But for classification, you won't have bounding boxes, but you will still have object files, which basically says helmet or head. And this should be classification for that. It will work. But right now, as we are doing object detection, we should go ahead and change this to detection. And now it became a detection problem. Training input. So this is where you give your training input. You basically converted your entire data, which is labels plus images, to TF records in your data pre-processing step. So here you simply add your TF records here, TF records input reader. Let's go to our TF records, copy this file. Paste it. And again, the same thing, because we're already in the current working directory. I'm just deleting this thing. So we are already on CB1 underscore workshop. That means the rest of all our, so CB1 will have TF records as a folder, which is this one, and then directly this one. And that's done. Then I think there is one more. Just give me a second. Just 1 second, guys. I think we should have one more input like this here. Just searching where exactly it is. Okay, that's okay. In case if this particular, it always depends on the model to model. So this pipeline.config file is with the model that we downloaded. So different models will have different required parameters. So yeah, before when I was doing, I mean, testing and all these things, there is a location to basically add like this, where I need to add this label.txt file as well, class underscore label.txt file. Yeah, there is a place where I can add that thing as well. But yeah, if we have a error message or something like that, we'll try again downloading the model and check why exactly it is. But for now, we'll just leave it there. So we have done editing the pipeline config. We are not doing the evaluation part, because as I told you, we cannot run two programs simultaneously on on TensorBoard, on Google Colab. So that case, we are basically skipping the evaluation part. But whoever is doing on laptops, I'm happy to explain them easily. So this is our TensorBoard. So we are at model training, right? So we are at model training, and we have extracted our model. We have edited our pipeline config. The next part would be putting everything for training. So we'll make sure that we are in the current directory, then create a training checkpoints folder. So we are creating one folder to store all our checkpoints there. So these checkpoints are generated while we are training. You say for every 1,000 steps you want to create a checkpoint, you can do that. You can specify that for every 1,000 you can get all these checkpoints, and you can constantly check your graphs using this tensor board. And suppose say you're happy to stop the training at 6,000, you already have a checkpoint already ready at 6,000, which is saved in your checkpoint folder. You simply do the stop. You can simply stop training and you can use that checkpoint. That's it. Happy. You don't have to complete your entire epochs. Suppose you say you put like 100 or 200 epochs, but within 5 or 6 epochs you got the results. You don't need to go to 100 epochs. Yeah, just using the graphs, we can stop them anywhere we want. So in order to get this running on our Google Colab, there's a small trick. That's because so these tensor board are run on a local host, right? We create a port, we open a port, we run it on a local host. However, this is a virtual machine and it's running somewhere in the cloud. We are using ngrok in Linux to forward this port as a public IP so that we can open it in our our systems. Right? We are just downloading that ngrok Linux thing. We are specifying that current the training checkpoints folder here, and we are running them just like this, right? Yeah, and then forwarding it to the ngrok thing like this and doing a curl. This would give us one link. If we click on this link, it will redirect to our TensorBoard page. Currently, we don't have the checkpoints right now. So we actually, the folder is empty. That's the reason we have this. But once we have the data there, it will show things like just like this, right? Or we can skip all these things and run it within the dashboard just using these two lines and specify our checkpoints. That's the other one way, and this is the second way. Just mention these two ways because for me, one way worked one time and the other way worked the second time. I just put two together and that's set up already. We are setting up this first only because when we run this file, it will execute this and go to the next cell, right? That's how Colab works. When we are doing training, if you initialize your training first, and if you don't initialize this graphs, this training will continue for 1 or 2 hours, and you cannot see your graphs because you haven't initialized them before. So it's better to do this first and then go back to your training. So I'll just do this. At the moment, no data, so it should give a blank thing. Just a second, should give it 1, 2, 3. Yeah, done. And let's go to the training. So within the same package, CV1 workshop, you have a training file, train_model.py. Yeah. So in the training file, so this script is, I mean, it basically takes model as input, model config file as an input. It will take all these other parameters like how many steps to train uh, on what hardware are you training? Are you training on GPU or are you training on CPU or a TPU? All these things. And how is your, where do you want to save your checkpoints? Uh, all these basic things. So you need to specify all these basic things within this flags. Right? All these flags are responsible to handle those things. Right? And so here, if you can see, pipeline config path, then goes your path. So the second one is always your what the number. I mean the value that you want to change is always the second one. So for everything, the second one is your the value that you want to change, and third one is the hint what exactly it is. So it basically says path to your config file, pipeline config file. So here, just remove this thing, close this thing, and in our pre-trained models, SSD mobile net, and this is the pipeline config that we edited right previously. Just go on that one, copy path, click on here, Control V. Again, the same thing. We'll just remove the this thing because we are still in the current directory, and that's our pipeline.config. Perfect. The second thing is your training steps. So as I told you, training steps, we can change it directly from this model, I mean train underscore model file, or we can specify it directly in your pipeline config. But when you do it here, so what happens is, we'll again go to the sketch. You have, suppose say you have 1,000 images. 1,000 images is your entire data set, and 100 is your batch size. 100 is your batch size. That means in order to complete one epoch, you need to rotate 10 times. I mean, you have to rotate the entire cycle, entire network 10 times. And you never specified epochs in any of the configuration config file, right? Epochs is never a epochs is never a parameter anywhere. So we specify epochs based on number of steps. So in order to complete 1,000, you need to at least go 10 times. When you go 10 times, this 10 is step. So one rotation is one step. Completing the entire data, completing all the 100, all the 1,000 records is one epoch. So that means 10 steps is equals to one epoch. This equation, right? And that's how you specify number of epochs. So for our current thing, we have batch size 8, and I think we have 50 images for our data set. So that's basically divide them, we'll get how many times we need to rotate the data set, and that's how you can set your batch size. At the moment, since we have Tensor board already running, which can literally tell us the loss graphs, everything in real time, we can simply put a really high number. Sorry. Yeah, we can put some good high number, and once we are satisfied with our whatever the loss curve is, we can stop it anywhere we want. Okay, I'm just putting 20,000 just for some number there. And training on evaluation on training data. So what this will do is, if you know cross validation, how cross validation works, if you have 10 data points, it'll sample 9 out of 10. I mean, it'll keep one as a spare, and then it'll train the entire thing on 9 and validate it on 1. That's still a part of training, but it is known as cross validation. It is not testing. It's still within the training itself. It'll keep 90% with to the train, and still keeps one for testing, and then again randomly shuffles that one part. So now what we are talking is in percentages. So 50 images in percentages, it would keep probably a fixed number of like 5% or a 10%. Not sure how much exact percentage it would keep. I think we have to change that, check that in the config file somewhere else. So something works like a cross validation. And I think here is where we see sample 1 of n evaluation example. So basically sample 5. You can put the number here itself. And yeah, this one is as well. 1 of every n training inputs examples for evaluation. So 5 for every 5 images, it will take one images for evaluation, which is fine. Yeah. Model directory is your output path. So you created training underscore checkpoints. You want to save your checkpoints in one folder, right? And this is your folder name. Checkpoints is already there. It's a parent folder. And inside your checkpoints, you need to specify your model folder. So what I do is, my personal practice is, suppose if I'm doing a model hack detection, I just put hack like this. And if I'm using learning rate of 0.001, I put 0.001 or something like this. And if I'm using batch size of 8, I put B8. And if I'm using any specific terms, I name them like that, so that whatever the folder is created will represent that particular instance. So next time if I run, and if I want to change the learning rate, and if I change it and update the same in the folder name, the second model will have a different file name. And you can toggle between these two within your tensor board. So within your tensor board, on the left side, you will have all the models that you are trained. And on the graph, you will have all the graphs for all the models. And you can literally select which model is best for you that way with the name. So I'll just specify something like this. Should be good. And evaluation timeout, we can skip because we're not doing evaluation. And TPU, we are not using TPU, we are using GPU. I'll explain where we are specifying GPU. We'll have only one worker running. It's not multi-threaded thing yet. We're not doing multi-threading, and we're not using mirror strategy. It's just one. And checkpoint. So for every 15, you can specify here, for every 1500 epochs, you can save your checkpoints. If you put 1,000 here, for every 1,000, it would save your checkpoints. The limitation of this is to save space. It will only save the last 8 checkpoints. Suppose you went 10,000, the initial 2,000 checkpoints were deleted. They would delete the initial checkpoints, and it will save the last eight checkpoints. That is, I think, from 2,000 to 10,000. Right? And this is all same. This is all same. No, you don't have to change anything here. And there you go. Here. If you're using a system with multiple GPUs, you need to specify all your GPUs like this. But in here, Colab, you're just using one GPU. So it's just GPU 0, right? And yeah, just this part, you have to make sure if you have multiple GPUs, you have to use this. Else, you can simply use the default one, which is this one. And that's all for the training part. Let's go ahead and train this model. Unfortunately, I think I have to restart my entire. I'll just try to run it, see if there are any errors. Let's see if I need to install TensorFlow again. Sorry. So in the initial these things, I mean the initial all these eye warnings, all these things, they're totally normal. Definitely can ignore them. So if you read them, I mean in depth, then you will know so what exactly it is accessing, all these CUDNN libraries, from where exactly it is accessing. Especially helpful if you're installing everything on your local machine if you have a graphic card. This is really, really useful because it will basically say this file is missing, unsuccessfully loaded this file. That means now you can search where can you get this file and which driver provides you that particular file to successfully install your CUDNN and Cuda. And trust me, it's not at all easy installing them on a machine for the first time. Definitely not. You can see here we are using a Tesla T4 graphic card on our Colab. So that's the graphic card they are allotted for us. And I think yeah, and the clock speed is around this. It's a 15 GB graphic card. However, even though if it's a 15 GB graphic card, most of the memory of this graphic card would be already allocated to different virtual machines. We wouldn't know what's the available memory on that particular graphic card. They're all shared graphic cards. That's the huge problem we face in Colab. Yeah, that we have to, unless we have Colab Pro Plus edition. Pro Plus is basically it'll allot one graphic card for you, and even the Pro version is still sharing, but it will give you extra time. And yes, here you can see we've imported them properly. It's all done. Yeah, it's already started training. So for every 100 for every 100 steps, it's going to give you your loss. So what is your loss? And loss is again combination of all the different losses, as I told you, right? It's a combination of classification loss, it's a combination of localization loss, which is four points, and regularization loss, it's a network loss, and the total loss is the combination of all these three losses together, and this is what it is. And you can also see your learning rate for that particular step. You can see that 100 per step time is 1 second. So that means if you want to train it for like thousand epochs, oh sorry, 1,000 steps, that basically 1,000 into one, but you can divide 1,000 seconds, 1,000 by 60, you can put how many? 16. It would take 16 minutes. So yeah, still pretty fast, I would say, because it's a very light model, and the batch size is really low. It's just 8. So this entire thing Is anyone else getting an issue with object detection? May I know where exactly, which cell exactly it is? Is it the model training file? Which file is this? Line 33. Oh yeah, line 33. Just a second. Line 33. May I know the error? What's the error? I think it's something to do with the object detection. I think it didn't recognize the package called object detection. Can you copy paste the error? Oh yeah. So it didn't recognize the object detection. So for that, what you need to do is simply go to your install object detection API, and yeah, try to run this all 5 cells again, especially this one, and that should definitely fix it. So it's just that you have object detection folder at that particular location, but it is not treating that particular folder as a, say, Python package. Now you're, while doing this Python install pip all this thing, you're making this object detection folder to recognize it as a Python package. The other thing what you can try is uncomment this thing and comment this file, this line, toggle between this and this. One should work after you install the API. Yeah, and I think let's go to our Tensor board and see what's happening with this one. Just restart. See, now you can see when I just clicked on this restart, what this will do is you have training underscore checkpoints folder, is it? So in this checkpoints folder, we in the model training file, we basically said to create a folder with this name to save all the checkpoints. So these are the checkpoints. Train is the file for TensorBoard. So events.out.tf events. This file is responsible for storing all your loss, your almost, in fact, many things. I'll show what are all the things it will store. It would also store some sample images, sample predictions, so many things. I'll show them. So currently the loss is like this. Let's see how it will go. And here you see, here you can see the name. So if you're doing for multiple models, if you want to try with different learning rates, different batch sizes, different configurations, you can specify them in the name so that you can visually see which model is what. So they would color coded. I mean, they would be color coded with different colors, and you can see the graphs like this, just like here. Tensor board. Yeah, something like this. Yeah. Now you can easily find which is your best model. I think we have a question. I'm getting the following error. Unable to open table file. That's because Arun, the checkpoint file name is you have to remove the dot data. So you have to remove the dot data, whatever the extension is. It's just until checkpoint -0. Awesome. Yep. And yeah, I think this would take little time, and I'll just keep it running so that will have our checkpoints, and then we can convert these checkpoints to actual model. These are still training checkpoints. We haven't I mean, we haven't done the complete training and exported them as a model. That's again a big part. So yeah, in case if you guys have any doubts and questions, you can just drop them there. And meanwhile, this is the training. I would say we have a really good classification loss. The classification loss is reducing good, but the regularization loss, that means the network loss, is very high. 0.77 is high. We want this value ideally to be around 0.00s, or at least 0.0 something. But that doesn't mean it's going to give really bad results. It's gonna give okay results. I mean, it's a very small model, right? This model, we can deploy it on mobile phones in real time. So that's a really small model. It cannot give you state-of-the-art performance, but still it's good. Still, it's really reliable. Also, yeah, once if you have if you come up with a really good idea of computer vision, object detection thing, and you want to train on a state-of-the-art model, but you need GPUs. Oh, I think there's so many questions I haven't followed on Q&A. Just give me a second. Could you please demonstrate the tensor board again? Yeah, sure. I think Arun have given solution for that one. How do you determine the reasonable values for training hyper? Yeah, I think I've given that one as well. Can we do object detection API for just the classification? That's done. Could you please demonstrate? Yeah, I'll do that. So is there any rule how we can decide batch size? Yep, that's done. It's done. And so this problem of Google protobuf.txt, can you please elaborate it? So what exactly happened there? My intuition is you haven't properly installed the proto files, which is, where is it? One second. Which is this: install all proto files using proto or proto installer. So this file would create such issues. So you say the object underscore detection dot protos dot random crop, right? Random crop is what the file is. So when we go into object detection, let's go to the object detection models, research, object detection, and in the object detection, protos, which is this, the random crop is what the problem is with. Let's search where exactly it is. Maybe in the pre-processing. Yeah. Image resizer could be here. Yeah, could be somewhere around these files. There's so many files, in fact. Yeah, just try to install this and let me know if it works. Let's go to our training and see. So we set it. So now this gave us a bit more information until. So I'm gonna close this, guys. I'm gonna close these things so that you can see this graph and a big thing. I think I have to use control. So yeah, learning rate is going up. Basically the warm-up learning rate from low to high. So at one point it will again go down. So yeah, it's just the warm-up learning rate that we have set. We can skip that. In fact, you can normally try with a normal learning rate in case if that's, yeah, if you have same classes in the Coco data set, suppose say humans, you're training on humans, but for a very specific task of detecting humans if they are fallen on ground. So you have collected people of on the ground, so they're the pictures of people on the ground, and you have labels of them, all these things. Now model already knows how to predict humans, right? They're all really good at that. Now it should just learn a little more, but it doesn't, I mean, you don't have you don't need I mean, the data set is almost same, right? It's just variation of people, so it can easily learn. You don't need warm-up learning rate for that. You can skip warm-up learning rate and simply put 0.1 or 0.2, 0.3, something like that. So 0.03, sorry. And this is learning rate. Where is our loss? Regularization loss is okay. Just a second. This is our classification loss. It's going down. It could be seen properly if it is like this. It's okay. It's kind of going down. But can we see it over here? Let's see. All right, this is much better. So that's the reason I basically said we'll use the NGROC one so that we can get it on a different browser, and it's much happier. So you can click on this, it'll open. You can see at where, I mean, you can see the numbers. I think it's too small for you guys. 1 second. Is that fine? Yeah. So these are the steps. So on the bottom, you see the steps. On this side, you see the loss. Then you can, if you know how to read it from just the numbers, you can simply go through your training logs and know how the model is performing. But in case if you want to see it, I mean, visualize it, this is the better way. The software is a really better way to understand how your model is going. So we have trained until 1000 steps. You can see it. You can see it here, I guess. So 1200 steps. It's still at 1300 steps. We can see it here. Just refresh. 1200. And yeah, we can track all our models using this graph. The other part is when you click on images. So what this will try to do is it will try to take your training images, but somehow I'm not actually not seeing any outputs here. But it should draw bounding boxes for these. It should draw all the bounding boxes for these, and you can see outputs while you're training itself. And for that too for every epoch. So for 200 steps, you now know what's the uh, bounding box for that images right at 200 steps. The reason I think it's not showing the bounding box yet is it didn't get the checkpoint. We told the model to save checkpoints for every 1500 steps. So it's not 1500 yet. So that's the reason it doesn't have a checkpoint yet. And once it creates a checkpoint, you can simply see the predictions for all these sample images. We can increase the count of the sample images just to, yeah.
Okay, so welcome back. Oh, we lost 2 people. Hopefully they'll come back. Look, like I said, I mean, I was gonna be happy with 10 people. Okay, I'm gonna lower everybody's hands, otherwise we're gonna be lost forever. Lower all the hands. Okay, so let's try to move forward.
Yes.
Did we manage to solve the problems? How many people still have problems? I think Alex still has problems. Makara still has problems. Look, guys, we will try to get to the... There was some strange humming going on. I'm not sure if you guys heard it. Okay. Sorry, I was saying I'm gonna be more professional and put the microphone in front of my mouth. What was I saying? Yes, we'll try our best to solve all the problems. I guess we're gonna have some more time at the end of this.
Yeah.
And then yeah, we'll just do it afterwards. I think that would be the best thing. Anyway, I give the floor back to Manas, and let's continue. Shall we clear up the questions first? Q&A. Could you show the changes that you made to the file? Is that already?
Yeah. Almost done. Yeah, they're all done.
Okay, then we had one more. From Alice, could you quickly show the edit for the pipeline config, please?
So yeah, I've shared this TensorFlow object detection API tutorial on our Teams group. So when you go to
share the screen.
Oh, I didn't share the screen.
No, you're not sharing your screen.
So this link on our Teams chat, and if you want to know where exactly we have to edit this pipeline config, you can go to configuring a training job here, and then here is your training config file. So it'll highlight the things where you have to do changes. There, the first thing is here, batch size, increase or decrease based on the memory, the fine-tune checkpoints, detection if detection similar to the ones, and then label.txt here, and this one here, this one here. Yeah, it will basically highlight all these important fields. Similarly with the training, this is the entire official API that you can follow step by step from your installation part to your data labeling, everything. This will include image labels, everything what we have learned today. This will have everything in documentation, right? And yeah, for those people who are installing TensorFlow on GPU, want to install on GPU on your laptops or desktops, you can use this step-by-step procedure to do that. So today it's more about implementing all this on Google Colab, which usually you couldn't find a better notebook that does everything on Google Colab, because using GPUs are really frustrating. So I thought, why not let's make a workshop directly on Colab itself, so that most of the people will have access to it and then can try object detection API. Usually it's definitely not possible on a CPU. Okay, moving back to our workshop. So we are still training this thing. So we are at 4,900 steps. So yeah, again, 5,000 steps. I'll quickly go to the tensor board. Here you can see my graphs. Okay. Classification loss, localization loss, regularization loss, and this is our total loss. So I'm gonna expand this total loss, and now zoom it a bit. So I've trained until 5,000 steps, right? The loss is still going down. That means model is still trying to learn things, right? We can definitely increase our training time and make sure it touches as low as possible. However, I'll just stop the training for now. Let's just check what the model has learned until now and make it like say it's a final model. Suppose say you've reached the last point and you want to stop the model. So let's go back to our notebook. For stopping, you can just simply stop. Simple as that. However, when you go to the training checkpoints folder, that is where all your checkpoints are, right? This is your model that you're training. And if you open that, this is all your checkpoints. As I told you, only 8 checkpoints are going to be stored. Rest of them are deleted. So we are still under 5,000 marks. So that means the first checkpoint is default. The second one is around 1,500. This one is around 3,000, right? And this one is around 4,500. So at the moment, this checkpoint is for 4,500. So if I stop training right now and use this checkpoint, that means I'm stopping the training at 4,500 itself, not 5,000, because at 5,000 I haven't saved my checkpoint yet. So either I can wait and until next checkpoint, or I can simply stop. So at the moment I'll simply stop it, because I think it's fine. It's okay. You can simply stop this. So that stopped. See, that stopped. And 1 second. Wait. Just give me a second. My laptop has frozen for some reason. Problems of Windows users. Oh, I think anyways the runtime is deleted, so we'll just restart. 1 second. Close everything. Okay, this is a different project. 1 second. Let me go and use this account. What's this? Just 1 second, guys. Yeah. So now I'll just quickly connect. So drive is mounted. This. So I don't have to clone all these things. They're already in the background. Let me check if I have this thing as well. It all run. It's done. Let's go to this. It's done. Let's do a setup. Oh, it's already installed. Okay, we don't have to build this every time. So we already have all the checkpoints from the training. So we have we have saved those checkpoints in our drive itself. So even if you lose the connection just like that, you don't have to worry because the training data is saved in the drive. Let's jump directly to the exporting part. How do you convert this checkpoints to a model? So I've shared a script which basically converts this thing, which is convert to saved model.py. So always remember the model end format is always going to be either .pb, right? .pb, saved model.pb. If it's a JavaScript model, it's going to be .js. Similarly, for PyTorch, it has its own extension. And similarly, YOLO, it has its own extension. So the TensorFlow object detection one is .pb. So even when you downloaded this SSD mobile net, this model, when you open that, you have something in this structure, right? Which has all the checkpoints, and it also has a saved model.pb. So this means it's a final build. So right now what we have to do is convert our training checkpoints similarly to that format, so that that model is going to be our the final model. So let's open the script from here and drag it like this. So yeah, this bunch of documentation, this script is directly from TensorFlow. I think I haven't done any modification to it. Yeah, it's a pure TensorFlow script from the object detection API itself. Nothing modification done. I've just changed the file names, and so this script will take inputs. So this first one is input shape. So we are not messing around with the input shapes because this is extremely difficult part of setting up this save model.py. The right now whatever we have is already set for object detection and key point estimation. So these two things, it's already set in within these tools, within this thing. And I also think, I don't think any of the models will require a different input and output shapes other than object detection. So almost all the models are for object detection. And here we specify our trained here we specify our model config, which is our config file from here. SSD mobile net, this one, config file. I'll just copy this, copy path, and I'll paste this. It's not the same one. Just to make sure, Control V, Control C, and then delete that thing. Okay, that's our config file done. The second one is trained checkpoint directory. That is the one which we basically trained checkpoints with. So this is our trained checkpoints. I open that. I give the model name. I gave a model name, this one. So I'll just copy this, copy path, just the model name, and give it here. And again, delete this the back thing. Yeah. So now what's happening is it'll automatically search for checkpoints, the latest checkpoint from this file. So all you have to do is put a slash so that it will check all the files after that folder. Okay, so inside that folder. And the output directory. Now we need an output directory. Suppose say I want an output directory. The output directory is trained models. So here we have training checkpoints, pre-trained models, so we can use trained models. Just refresh it. So trained models is empty right now. Trained models is the models that we trained. We are using this folder to save our models. So we simply put, we simply put the path there. Copy path, and we put it here and delete the rest of the thing. What you can do is here, so once you specify, can you guys see my screen properly? Yeah. So once you specify this folder, trained models, it's trained models. My bad. Let's copy it again. Copy path. Control C. Train models. Hash. You can give any model name that you want to give. Just like you've given hat 0001. This thing, I'll probably give the same thing as well, because I would know what that particular model is trained on. 001, batch size 8. So that's my model name. And yeah, that's it. Nothing more. Just inputs, config file, input your checkpoint, input your output your model. And when you run this, it's going to slowly create the model and give us the model file within our trained models directory. you will find so many warnings and something like unsupported, something like this. That's all still fine. It's just that few tensor shapes may not convert properly. But then TensorFlow will optimize them and convert them. Yeah. So that's done and saved. So right now, when you open trained models, you would see this mod. And this has the similar ones which we have for SSD mobile net. It's checkpoints. You open checkpoints, you have check the latest checkpoint. Save models, you have assets. So there's nothing in assets, that's fine. So variables and the saved model.pv. It also have, it just basically copy pasted the pipeline.config over here with the changes that we made, with all the batch size, all these changes that we made, it basically pasted over here. That's it. That's how you export models to, export your checkpoints to your models. Very simple, just one script, done. Now comes this inference. Now, how do you test that your model is working, right? That's a really important part. And how can you run your models in real time? Yeah. So what I'll do, there's a small script. It's a small Python script. I'll go through the script. So initially, import OS. Oh, you guys know the OS thing. It'll basically collect files from your operating system. Any read-write operations can be done using OS. You're importing TensorFlow. Uh, you can skip that actually. Pathlib, it's a dependency package. Google, CV2, we can use it on the desktop or a laptop's Jupyter notebooks, but Google Colab doesn't support CV2. That's because the output of a CV2 is a window, right? It's a pure window, and we cannot open any windows on the web browser. So that's the reason we cannot use a general OpenCV. So we have to use a Colab version of OpenCV, which is CV2 underscore imshow. Just one package. This is uh, so it's a GPU programming. If you want to do an inference on the GPU, so you need to make sure that you set your memory growing so that your entire GPU is not allocated just for doing this job, right? If you have like 10 gigs of memory and you're using 10 gigs of memory just to do video streaming, that's a lot of a wastage, misusing of GPUs, right? So this will ensure that if your image takes only one gigabyte of processing, so it will only allocate one GB of GPU for whatever your code you're running. It won't allocate the entire GPU. So that's a huge problem, especially if when I'm using a Deakin server, which has like 10 GPUs, and if another guy is also using all these 10 shared GPUs, if he doesn't put this one, or maybe most of the GPUs are allocated to him, even though if he's not even using them. So that's a huge problem. Some people miss that, but I just wanted to add it so that the other person who's using that GPU is happy and you both use together. Uh, so here, all we need is to provide the model file, the model path. So simply let's go and train models here, saved model. Just copy the saved model thing, copy path, and then put it here. That will automatically find the saved model on .pv file because it's on the same folder. Now we give label underscore txt, which is our classes. So these classes are on here. They simply say if If you get an output 1 for hat, so it will simply say 1 is head, or simply 2 is helmet. So the outputs are always going to be numbers, right? So it will convert numbers to text for displaying. Yeah. Oh, I've just noticed one small thing. I think I have to delete this one. That's because I'm adding the saved model here. So it's like this path plus saved model is the final path. Or it's I mean, it's fine. Like, or I'll just let's keep it that way. No problem. And yeah, I can I run it? So yeah, so we have loaded the models. So whatever the model that we created, we loaded that model at this name. So this is the function tf dot saved underscore model dot load, and you give a path to the PB file. So this exact folder, you need to give the path here and use this function to load your model. And if you pass an image to this model, it will give you a prediction output. I'll show how this prediction output looks. Before that, we just loaded the model right now, and as it took around 8 seconds just to load our model, and this is only one time, right? The second one is you read an image, you pass this image to your model and get the predictions out. So yeah, we are importing some basic libraries, NumPy, Matplotlib, and few warnings to check what's happening with the we are basically ignoring all the warnings. That's fine. So there is a function here which basically loads a NumPy array, load an image file into a NumPy array, because at the end of the day, this whatever the file that you're using, you need to convert that into arrays, right? Models will only accept image tensor, shape of an image tensor, and image tensors can be created only using arrays. So now we are converting your image to array using np.array of image. That's the entire image. And now you are simply converting them using convert to tensor. And once it is converted to input tensor, you're passing it to the model. This is the model, and you get the detections back. I would like to basically run this and see the output. Okay, so that's the detection. So these are all the detections that you get from running. I know they're super complex. I mean, there's so much data just for one picture, but I'll break down what exactly this information is. Okay, so these are the detection scores. I mean, this entire dictionary of detection scores is for 100 boxes. Okay, by default, model is going to predict maximum of 100 boxes. So even if there are 4 people on a picture, it would still predict 100 boxes, but only 4 people, only 4 boxes will have higher confidence. The rest will have very least confidence, right? Similarly, same that thing. It provides 100 boxes, and then it gives anchor points, anchor indices. That is no, we actually don't need the anchor points. Yeah, detection score. This is the detection score of each box. So that means the first box is detected 99%, second is 99%, third is 99. And when you see the fourth, fifth one, now you can see the accuracy goes zeros, right? Almost zeros. So that means all the heads and hats are already detected here, right? And the rest of all are random digit, a very low random digits of epsilon, value of epsilon. And these are the bounding boxes for each box. So this is for the first box, and this is nothing but this core, this box, and this core, the second box. Third, you can basically map it, right? It's in the serial order. All the things are in serial order. Now comes is the class. So these are all for 100 boxes. Detection multi-score class. Oh no, the multi-class score, we can skip that. There's so much. Yeah, detection class, we need this one. 2, as you know, 2 is basically helmet. 2 is helmet and 1 is head. So depends upon the confidence, you need to filter them uh, based on the thresholds, whatever threshold you said. You said, suppose say 70% as your threshold, you need to filter all these values using score as 70%, and then you will basically remain with only 5 or 4 detections with all as hat or all as head based on that. When we go down, that's it. That's done. Let me visualize this. Just a second. How can I visualize this? Okay, I'm just so now that you have seen the detection and all the results, that's how you get the detection results for all the TensorFlow object detection models. It's same for all the object detection models, and that's the format, in fact. And now here we have to display stuff, right? To display stuff, I'm just using this package. TV2 info. I'll just put it over here and open it. And this is the file name that I'm passing. I'll explain this, the visualization part after I do this. I'll just put it here, run it again. Let me see. So yeah, now you went into, you got the detections here. You pass the input tensor to a model and you got the detections, right? Once you get the detections, you are now basically getting the number of detections. So now you have 100 detections, right? This is the 100. So you can see the int 100, you can see the value there. So there are 100 detections. And you're also going through each detection using items. So items is nothing but, one second, it's a little complicated one. So uh, oh yeah, so you just have 2 classes, right? You're iterating the entire thing based on your items, and at the end again you get the same detections back. So from these detections, you're basically saying number of detections 100, you're just copying them back to number of detections so that you can pass the entire dictionary over here. We know we have to convert this into integers. You have to do some type data conversion, because whatever the current data is in float, uh, you can see, right, in the detections it's dot something. So it could be minus, it could be, so some values are in minus, some values are in plus, but this will ensure, int64 will ensure they're all in positive integers. And yeah, and basically you're copying them again like this. This visualization script is again by TensorFlow. You can still write your own scripts using OpenCV. You can use NumPy, Pandas, and all these libraries. Just all you need to do is you need to know how to use this detection data. So whatever the large data I've shown you, you need to know how to use that, extract the data that you want, and use it for drawing boxes or drawing circles. You can do any stuff with that, with those things. Okay. So I've drawn these things. So this will take boxes as input, classes as input, score as input. It will do all the, I mean, necessary calculations. It's a very, very big function. You can still, this is your minimum threshold. If I put 70% here, 0.7 is 70%, and then run the cell. So above, only the images with are above 70% are displayed. So that's still okay, not I mean accurate. I would say that's because this image is from the training set itself, right? It's no big deal. So I just took an image from the training set. Obviously, it's going to give us 100% super good results because it's the model has seen the picture. Let's now try some picture from online. Had construction workers or anything like that. Let's see. Oh yeah, let's see with this one how we go with this one. Save image as. Let me just see. Test. Downloads folder. Save them. I'll just try to upload this one. Where can I upload this? I'll simply upload this in the file itself. So I'll just do this one, upload, test, open. Yes, that's fine. Where is it? Test. Is this the image? Yep, that's the image. So right click, copy path, and I have to copy this path over the image path, right? It can accept PNG, it can accept JPEG, it can accept all these image file formats. That shouldn't be a problem. So yeah, it's still accurately giving. I mean, yeah, that's still fine, right? That's still fine. Let's find some other images just for the head. People. Yeah, I mean, definitely not sure if it's going to handle, but let's check. Yep. And I'll click upload. Just Control V. There's this guy here. Copy path. Oh, it still says helmet. Let's see why. So the one is never an option. So this means the classification loss is not that great, but the regression loss, I mean, finding the bounding box is good. It is able to recognize the head and draw a box for it, but it is not good at recognizing what exactly what exactly the person is. I mean, the classification is. Maybe it needs a bit training, or not sure why exactly. Yeah, why exactly that thing is. Also to remember, we've just trained this thing only on 50 images, just 50 images. But still, I would still say at least the bounding box loss is really good. Yeah, may not be classification because that's a new thing. The model doesn't know what's helmet and what's head before, but model definitely knows how to detect faces. So it did its work right. Probably a bit more training and bit more data, we could really get this really accurate. Yeah. I also have a really good accurate model already trained a couple of months before for a different purpose. And yeah, next I will basically upload that model and show you guys really good results on that model. Can you try maybe a cat or a dog image? Yeah, sure, why not? Cat image. Let's do this one. Oh, that's too small. Let's do this one. Oh, sorry. Save images. Let's do. Oops. No. So that's JPG. What we can do is simply identify. See, yeah. At least it did. It didn't recognize it as a human. But yeah, it definitely needs a lot more training and a lot more this thing. So next I'll show you how we can run our model on a video, on a continuous video, right? And so this is a video that we used for our prototype for making. Yeah, so it's a really long one. Yeah. So the entire video is on AWS as a .mp4 .mp4 format. What I'm simply doing is just copying that link, whatever the video is on AWS. I'm using cv2 video capture function in OpenCV, and then obviously I cannot display this in real time on Colab. However, it's really easy to do it on our Windows machines or Mac machines. But on Colab, what we can do is we can run detections on our model and create a different video with the detections on it, so that we can just download the video and then see what happened with that detections, right? So this is there, and I think we are good to go. I'll just simply click on this. So for every frame, it's going to do that thing. So every frame it's going to take a prediction and like get the results, draw the bounding boxes, push it to a model, right? I mean, a video writer. So we are using a video writer here, which is this cv2.video writer. It'll write every frame one by one by one. So meanwhile that's done, what I'll show you is the shared. I mean, so this is one model that we created for a client. It's the same. I mean, the purpose is the same to detect hat and wets, but it's trained on much more images, at least like 4,000 to 5,000 images, and fairly accurate, I would say. So let's use that model to see the predictions. How we are going with the predictions for that for our thing, right? So so I can access these models here. They're here. Yep, I can access them here. I need to make sure that if I have to set this within this project directory. So I'll just go back here, this one, I'll drag drop inside that, just went inside, and it's over this. So let's go back to the file, just refresh that like this. And now I have hat detection, all these things here. I can simply use this particular folder to run my predictions on. This has all the necessary files that I need for a deployment. It's taking time. We still couldn't see the output file here because it's a drive, and you can only see once the entire thing is done, and then it will be uploaded to the drive. But we can see that file here. It's around 300 MB so far, so I'll just stop it for now. That's too much. Okay. Let's download them. Oh, might take a lot of time. Or just close it like this. And then see it over here. Yeah. Hopefully we can play AVI files. Oh no. Oh, not anyway. Yeah, at least this is fast. It's in slow motion. That's because of the writer. We can increase the fastness of that. But yeah, obviously the results are really poor because it's a, I mean, we have just trained it with 50 images, that to only just 5,000 steps, right? But still, for some parts of the video, we can really recognize them for every, at least the bounding boxes for every frame. It's done. Let's try with my oops. It's a much bigger model. Maybe I've never tested it on Colab. It's a much bigger model. Let's see if it works or not. Oh yeah, 28 seconds to load. Not bad. On a cat image. So cat image, it didn't give any predictions, luckily. Let's try with test. Oh, where is it? Test.jpg. Please continue. Yeah, sure, I'm there. Head. Oh, that's bad. 1 second. Probably it's the problem with uh, the uh, I mean, my model might have one as head and two as helmet. Let's see if I get helmet for the other one of this guy, then yep. Oh, for this we didn't even get anything. Okay, that's weird. Or let's just delete this one. Delete this one. Yep. And try to run it on that. It's done. Oops. Oh yeah, it's the same issue. So the helmet is basically classifying as head. That's just the label difference. So one became two and two became one. Except that it's yeah, that's fine. We can always change the those labels before we, I mean, specify it for a label.txt there. So we can simply change that in here. So we can put it this 0 and then put this to 1. If we have detection outputs, this detections. Okay, it's 1, 2, and 3. So there are 3 classes for my model, not 2 classes. I'm not sure what's the third one, but this is 1 and this is 2. Save it. And run it on test. Yeah, unfortunately, I have to load the model again because it's going to take this as input. Oh, maybe not, but let's see.
So maybe what happens, maybe we can try to see if anyone has any questions.
Yes.
About this part. So let's try to optimize the time. So Arun was asking, was wondering if instead of fine-tuning the whole pre-trained model, we freeze the initial few layers and fine-tune on just the last 1 or 2 layers, fully connected ones.
Unfortunately, this API wouldn't allow us to do that thing. But if we have our own models, then yeah, we can do it. Not with this TensorFlow object detection API. Or maybe I haven't seen that. A part where we can disable training for the initial layers. But yeah, I will do some research and let you know if we could do it using API.
Did something come out already? Or?
Yep.
Oh, okay.
Yep. Anything else? So converting these models into TensorFlow JS models, we'll discuss that tomorrow or day after tomorrow once you guys are familiar with this object detection thing. We'll see and deploy them as TensorFlow JS models. And you guys have any questions?
Okay, so can you go back to the image of the guys with the helmet?
Yeah.
Okay, so this is probably the big question that comes up. What is the meaning of the number? This is a very important question.
So the number is basically how confident that picture is. So that box is 80% confident that it's a helmet. And it can literally change. I mean, we can literally change the number just by changing the label, and it will simply say it's 80% head. So in data science, these numbers are what you how you visualize them. What I would say is it's just the score, the bounding box score or the classification score. I can simply put bounding box score as 80%, and people can literally see higher accuracies here. But what we need is the classification accuracy to be here, which is 80% helmet or 90% helmet, 80% head or 90% head, something like that.
So this is an actual, so this is the confidence. Yeah, so this number is very important when you need to explain to people what it is that they're looking at.
Yeah.
So the score, meaning that if the model says it's 80% confident, it doesn't really translate in 80% chance that it's right.
Yeah, not in real life.
Yeah,
It's just that on that particular data set. That's it.
exactly. So
Yeah.
one thing that you need to do then is to set up your own type
Benchmark.
of test. Somehow you need to go and test it yourself. So how
Yes.
would you go and test it? You would go and actually, pass some new images and look at
Yeah.
them and say, um, how many false positives or how many false negatives do you get? That is the score that you kind of need to deliver to your client if you need to, you know, do something for a client. If a client
Yeah.
comes in and say, I need an application that 90% of the times can find a cat in a picture, you can't go and use this score to say, oh, our algorithm reaches 90%. It's not that.
Yeah.
A lot of the normal people, yes, a lot of the people will understand that your score of 90% means that 90% of the time you can find the right one. It's not.
It's not.
To get a score like that, you actually need to sit down and test it and see in real life what is your actual score. 90% means that you put through, I don't know, 10 pictures of cats, and at least 9 times out of 10, it recognizes there's a cat in it. That's
Yes.
what 90% means.
Yes. And even the state of the state of the art models, when we go to the object detection API, and when we go to the model zoo, which is this one, you can see the accuracies right here. The maximum you could see is 50. There's this 50, and that's considered as the top line model. I mean, it's literally the state of the art this year on the Coco data set. That's because, yeah, the accuracy number for this particular thing is just that much. The images that has is really, really huge. It's a really huge data set. Uh, so the labeled images are around 200, but in 200 in all these 200K images, there are 1.5 million objects. So whatever those small objects, one hat, one head, there are 1.5 million of those things, and they're classified as 80 categories. And yeah, so on this data set, that accuracy is good. People try to compete with, I mean, if I say, if I get 45% accuracy, if I say someone who's not from data science, he would literally say that's a fail model. But if I say 45% accuracy on Coco data set, or to a data science person who knows what is Coco data set, then that guy would literally say it's an amazing model, right? Yeah,
Okay.
this is why
We have
this.
more to talk about in the inference part.
Yes, Alicia.
No, I mean, did we reach the end of the inference part?
Yeah, we reached the end of the inference part. So this one is just for the video,
Mm-hmm.
but later on I'll show different techniques to how to use those boxes. Now say you just got the bonding boxes. Suppose when we are dealing with perimeter detection, suppose you want to draw something on a picture, and you want to check if a person, you're drawing a bounding box for the entire person. You want to check if that person is on uh, a restricted area. So now what you do is you have 4 points, these 4 points. You calculate the center point, and consider that as foot of the person, right? Now you locate where exactly this foot is uh, within the box. So if it is in the box, you simply say the person has stepped onto a restricted area, and if it is outside the box, you simply say you won't trigger any alarm. You check that using bitwise operators. It's more uh, OpenCV. You will get to know once you use OpenCV all the functions of OpenCV and all. You'll easily get to know how you can manipulate these results to fulfill our task. Yeah. So I think, yeah, for now I will definitely not go much into uh, the implications of these proper detections, because it for you guys, you need to come up with ideas, and if that particular idea needs a specific say very very specific thing which can be done only using computer vision or OpenCV libraries, then I'll, yeah, definitely help you guys what needs to be done on top of this detections. I think the important part is idealizing your problem, and then thinking as a data scientist and collecting data, labeling them, putting it into training, and getting the model. So the idea part is the most important part.
Yeah. So I think what we need, I think one thing that we never mentioned is that is very important is also being able to engineer our ideas. So unfortunately, there is this concept that we have infinite resources. Once you get into data science, you will understand one thing: your infinite resources are extremely finite or finite. I can't remember. Finite resources. Um,
Yeah,
so
very
even
limited.
having you can go out and you can go buy an NVIDIA 3090 just to realize that it will still take you hours to train a model. um,
Yes,
the models that we train for our system, we train them on the Saruman system, which has how many GPUs?
eight GPUs, and each GPU is 12 gigs,
Yeah.
and it has a RAM of around 128 GB. It's a
So
40 core processor.
yeah, so you think that that would be, you could do everything on it. That's definitely not the case.
Yeah,
Um, and when we actually make, so that's the training part. So that's that's what we need to see when we train, which is fine. We're looking at a lot of data. But the other problem is when we create application and services. Imagine if we had to create an application that was needed 8 GPUs in parallel to work. That would be extremely, extremely expensive. Um, so at our level, we're looking at perhaps to try and use the minimum amount of resources um, to make things happen. And so we really need to play with everything, and we have to think about how to engineer our things rather than let's just increase the resources. Um, and I think the clearer example was when me and Manas had to solve the problem of multiple models coming in. Multiple models being applied to the same image.
yeah.
Um, what are the things beyond the data science that I can go and touch to go and solve that problem? For example, do you need to do um, real time on a video of 24 frames? Perhaps you don't need it. Maybe you can just do 12 frames. Or I can't remember. Manas, do you want to talk about one of the things that we solved? Uh,
Yeah. So few more. So we've run 4 models parallelly. So one is for estimating head detection and hat detection. Second one is the vest detection, construction vest. Third one is to check if a person is running, fallen, or a perimeter detection. That's the third one. And the fourth one is a deep sort algorithm, which is, suppose say you got 3 bounding boxes like this. Uh, 1 second, guys. suppose say you got 3 bonding boxes like this, but in the very next frame, you still get the 3 bonding boxes because there's no much movement, right? However, you need to know that this bonding box is the same person. There's no assigning of IDs for these bonding boxes. So the first bonding box is not always this person. It's always the highest confidence, and the confidence can be randomly done for every single frame. So in order to keep a track of the bonding boxes, we also used a deep sort algorithm for that. So that's 4 running on single GPU on a single image at a time. Then we face so many issues that the first model takes a lot of time to get the results compared to the third model. We have tried parallel processing of all the 4 and then getting the outputs, but then uh, by using these parallel processing, Python parallel processing functions, uh, they cannot take our entire model as a GPU model, uh, like a parallel inference. So we need some GPU parallelization for that. So what I've created is, so you guys saw this, right? So this small 3 lines of code literally changed the game. So what I did, I I took one GPU. I've created I created blocks, logical blocks of GPUs, suppose say 4 logical blocks, and allocated each logical block to one model so that it treats that logical block as an independent GPU. We can get that thing on TensorFlow GPU.
Okay. I think I just wanted to basically say
Yeah.
that in data science, you always need to keep a good data scientist is a person who can solve a problem. A really good data scientist is the one who actually, a data scientist is a person who can solve problems with perhaps knowing all the variables and applying his knowledge. A really extremely good data scientist instead is a person who has to face problems that he has not faced before and can come up with the answers. So that comes from experience, that comes from creativity, that comes from passion as well. And so that is a difference. So that's why I think Manas is really great. He still can grow. He definitely has to grow a lot.
Yeah, a lot.
But he's on a way to become, really good, which we hope he will. At least I hope. Anyway, so I think we got to the stage where we need to start wrapping up.